What if time suddenly stopped? Imagine the world instantly freezes. Cars stop dead in the middle of an intersection, birds hang motionless in the air, and every single person around you becomes a living statue. You're the only one who can still move. At first, it feels like a dream come true. You have the ultimate power, the ultimate freedom. You can walk through a world that is yours and yours alone. But the terrifying reality of what happens next is a nightmare no one ever imagines. This isn't a superpower. This is a prison. And you're its only inmate. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The fantasy of a frozen world. For the first few moments, it's absolutely intoxicating. That kind of power is absolute. The world, in all its chaotic, beautiful complexity, is paused just for you. Think about it. No deadlines. No responsibilities. No rules. What's the first thing you'd do? You might just walk. You could step off the curb and stroll right down the middle of a 10-lane highway. The cars are frozen, their drivers a gallery of emotions. One is mid-laugh, another is singing a song you'll never hear, a third is captured forever in a moment of road rage. They're all statues, and you're the only visitor in this silent museum of one single, perfect moment. The possibilities feel endless. You could wander into the most secure bank vault on the planet. The lasers are just harmless, solid beams of light. The pressure plates are just tiles on the floor. The guards are stone. You could learn the world's most guarded secrets, reading documents left open on desks in government offices, peering over the shoulders of frozen generals. You're a ghost, an invisible observer of a billion captured lives. And what about the little things? You could finally catch up on sleep in the plushest bed of the most expensive hotel. You could borrow a masterpiece from the Louvre and hang it in your living room, just to see how it looks over your sofa. You could spend years just learning, reading every book in every library, teaching yourself every skill you can imagine, from playing the piano to quantum physics. You become a master of everything, a scholar of a world that no longer moves. You might even try to be a small-time hero. You see that coffee cup hanging in the air, about to drench an unsuspecting woman. You gently pluck it from the air and set it on a table. You see a child's balloon that slipped from their grasp. You catch it and tie it back to their wrist. You're the silent, unseen god of this static world, correcting tiny mistakes. For a while, this is your playground. A universe of beautiful, silent things where you are in complete control. But this perfect fantasy is built on a lie. And the first cracks are about to appear. The dream is about to curdle into a nightmare, and you'll soon realize you're not in a playground. You're in a tomb. The nightmare begins. The laws of physics. Your first clue that something is profoundly wrong isn't some dramatic event. It's a simple, biological need. You try to take a breath. And you can't. See, when time stops, it's not just people and cars that freeze. Everything freezes. Every atom in the universe is locked in place. Air isn't empty space. It's a fluid of nitrogen, oxygen, and other molecules zipping around at hundreds of miles per hour. We breathe because it's in motion. But now, it's not. The air around you has become a solid, rigid crystal. When you try to inhale, you're trying to pull a solid wall of matter into your lungs. It's like trying to breathe concrete. You might have one breath held in your lungs from the moment time stopped, but once that's gone, you'll start to suffocate. Panic sets in. You try to move, to run. But you can't. You're encased. The frozen air molecules are pressed against you from every direction, holding you like an insect trapped in amber. To move, you'd have to physically shove trillions of static particles out of your way. The force required would be astronomical. But let's say you have superhuman strength and manage to push forward. The results would be catastrophic. The friction of your body grinding against unmoving air molecules would generate incredible heat. You wouldn't be walking. You'd be creating a plasma trail of incinerated air. Each step would be an explosion, a flash of blinding light. You'd be a walking disaster, carving a path of destruction through the silent world. Even then, you couldn't see where you were going. Because the world is now perfectly, absolutely dark. Vision works because photons, particles of light, travel from a source, bounce off things, and hit your eyes. That process takes time. But now, the photons are frozen too. The light from the sun, the street lights, a phone screen, it's all just hanging there, useless. No new photons can reach your retinas. It's a blackness so complete your brain can't even process it. And then there's the silence. A silence more profound than any soundproof chamber on Earth. Sound is just the vibration of molecules. With the air frozen solid, those vibrations can't happen. Sound doesn't exist anymore. All you can hear is the frantic, useless thump of your own heart inside your skull. Blind, deaf, and suffocating. That's the reality. The fantasy of being all-powerful lasts for a single, horrifying second. The nightmare that follows lasts an eternity. Okay, let's grant you a miracle. Let's say a small, 1-meter bubble of normal time exists around you. You can breathe the oxygen in your bubble for a little while. You can move your arms and legs. But the moment you try to step outside it, you hit that wall of frozen time. And you're still blind. You're still deaf. You're trapped in a 1-meter cage of normality, in an endless, dark, and static universe. This isn't freedom. This is solitary confinement on a cosmic scale. The Long Descent. A chronology of loneliness. Hour 1. The sensory prison. The initial panic fades and a new kind of terror creeps in. Thanks to your personal time bubble, you can breathe, but the sensory deprivation is absolute. You're floating in a void. You wave your hands in front of your face and see nothing. You scream, but the sound dies within your 1-meter sphere. The silence is a physical weight. The darkness is a suffocating blanket. Starved of external input, your brain starts to turn on itself. This is a real psychological phenomenon. People in sensory deprivation tanks report hallucinations and anxiety after just a short time. For you, this isn't an experiment. This is your new reality. You start to see faint flashes of light, your optic nerve just firing randomly. You might hear a phantom ringing in your ears, the ghost of a sound in a world where sound is dead. You are totally alone with your mind, and it's already starting to fray. Day 1. The burden of movement. You learn how to get around in this new world, and it's a painful, exhausting process. To see anything, you have to move. As you take a step, your bubble of thought time moves with you, colliding with the frozen photons that were already in that space. Your eyes get hit with a chaotic, meaningless blast of light from a single, static instant. It's not vision, it's visual noise. Then, blackness again. To see, you'd have to walk constantly, sweeping up frozen photons. Walking becomes a bizarre and exhausting form of echolocation with light. Every single movement is a Herculean effort, like wading through cosmic molasses. You spend your first day just trying to get home, stumbling blindly, recognizing your path only by the searing flashes of static imagery. You pass the frozen forms of your neighbors, your friends, your family. They're inches away, but they might as well be on the other side of the universe. You can't talk to them. You can't touch them. They're just monuments to the world you lost. Week 1. The onset of true loneliness. A week in, the novelty is long gone. This power isn't a gift, it's a curse. The prison is real, and the true nature of your situation finally settles in. You are utterly and completely alone. Humans are social creatures. Our minds are wired for connection. Without it, we break. You start talking to yourself, not out of habit, but out of a desperate need to hear any voice. Then, you start talking to the statues. You stand before the frozen figure of a loved one, their face caught in some mundane expression. You tell them about your day. You tell them how scared you are. You plead with them to move, to blink, to show any sign that they can hear you. But there's nothing. Just a cold, indifferent stillness. Their unblinking eyes stare right through you. This one-sided conversation is your only social life. Loneliness is no longer a concept. It's a physical ache, constantly gnawing at your sanity. Month 1. The mind's rebellion. After a month, your mind starts to rebel. To cope with the absolute lack of anything, it starts creating its own reality. The hallucinations become more vivid. You don't just see flashes of light. You see fleeting shapes in the dark, figures moving at the edge of your perception. You hear whispers in the crushing silence. Are they real? Or is your brain inventing companions to save itself from the abyss? You develop rituals to keep the madness at bay. You wake up when your watch says it's morning. You walk a specific route. You eat frozen food, though you can't cook it, smell it, or really taste it, since all those things rely on moving molecules. It's all a pale imitation of life. You become obsessed with unfreezing someone, trying to will them back into motion, just to have someone to share this hell with. But physics is a cruel god. Nothing works. The last flicker of hope dies, leaving you in an even deeper darkness. Year 1. The sole agent of entropy. You notice something else. The world is perfectly preserved. A flower frozen mid-bloom will never wilt. A building will never crumble. In this static universe, there is no decay, no entropy. Except for you. You are the only source of change in the entire cosmos. Every step you take, every door you push open, you're introducing chaos into a perfect system. You are the only thing that causes the universe to age. You are a walking, breathing agent of decay. The world is a perfect crystal, and you're the flaw threatening to shatter it. This realization brings a new, horrifying weight. To preserve this frozen world, you must stay perfectly still. But if you stay still, the sensory deprivation will drive you mad. It's an impossible choice. A decade. The god of a dead kingdom. 10 years pass. What are you now? You've walked the entire globe. You've stood at the bottom of a silent ocean, the water a solid block of blue glass. You've climbed a frozen Mount Everest. You've read every book and learned every secret. You have all the knowledge and power in the world. And you have nothing. Knowledge is meaningless without a mind to share it with. Beauty is hollow without another eye to appreciate it. Power is a joke with no one to rule over. You're a god of a silent, static universe, and the existential dread is the very fabric of your being. You start to question if you're even real. Is this all just a dream? This is the core of solipsism, the philosophical idea that only your own mind is sure to exist. For you, this isn't a thought experiment, it's a lived reality. What happens when you, the last flicker of consciousness, finally die? Does your death allow time to flow again, the world resuming its course with no one ever knowing that for you, an eternity of lonely hell has passed? Or does your death mean the true end, plunging the entire cosmos into a permanent, frozen state from which it will never recover? The science of the impossible. Okay, so what we've just walked through is a narrative nightmare, right? Pure fiction. But it's a nightmare that brushes up against some seriously mind-bending, real-world physics. To get why stopping time is so catastrophic, we have to ask a more basic question. What even is time? For centuries, we saw time as a cosmic clock, ticking at the same rate for everyone. Then along came a patent clerk named Albert Einstein, who completely shattered that idea. His theory of special relativity showed that time is not absolute. It's relative. The faster you move through space, the slower you move through time relative to someone standing still. This isn't just a theory, it's a proven fact. Astronauts on the International Space Station age a tiny fraction of a second slower than we do on Earth. In a way, we are all constantly messing with the flow of time just by walking or driving. This leads to a deeper debate. Is time a fundamental part of reality, or does it emerge from something else? Many physicists argue that time is inseparable from change and entropy, the universe's tendency to move from order to disorder. Think of it. If nothing ever changed, how would you measure time's passage? Without change, the concept of time might be meaningless. From this view, stopping time isn't just pausing a clock, it's halting the engine of reality itself. But here's where things get even weirder. There's a real phenomenon in quantum mechanics that sounds eerily like freezing something just by looking at it. It's called the quantum Zeno effect. Imagine you have an unstable radioactive atom that will eventually decay. According to quantum mechanics, as long as it's unobserved, it's both decayed and not decayed at the same time. The act of measuring it forces it to choose a state. The quantum Zeno effect says that if you observe that particle over and over again, super fast, each time you confirm it hasn't decayed, you essentially reset its quantum clock. If you could do it fast enough, you could theoretically prevent the atom from ever decaying. You'd be freezing it in place through constant observation. This has actually been done in labs. Now, this is a long way from freezing a person. The effect only applies to tiny quantum systems. But it's a profound idea. It tells us that at the most fundamental level, the relationship between watching something and the passage of time is far stranger than we ever thought. The solipsistic abyss. The physics are terrifying, sure. But the real horror isn't about photons or air molecules. It's about being the last conscious mind in the universe. It's a philosophical nightmare known as solipsism. Solipsism is the idea that your own mind is the only thing you can be sure exists. Everything else, the world, other people, could be an elaborate dream. Normally, that's just a late-night thought experiment. But for you, in this frozen world, it has become your horrifying reality. You are the only one who thinks, feels, and experiences. Everyone you ever loved is now functionally an object, a philosophical zombie, something that looks human but has no inner life. From your point of view, you're the universe's only observer. This creates a terrifying paradox. Does the universe even exist when you're not there to perceive it? The entire cosmos might as well be a complex hallucination generated by your own mind. This leads to the ultimate existential crisis. What is the purpose of existing with no one to interact with? If you write a symphony that no one can hear, does it make a sound? If you solve the mysteries of the universe but have no one to tell, does the knowledge mean anything? You have infinite freedom, but it's the freedom of a single atom in an empty void. Your own identity would begin to dissolve. Who are you without the people who know you? We define ourselves through our relationships and our roles in society. Without others, you are simply a thing that is aware, a lone flicker of consciousness in an ocean of oblivion. People in extreme isolation, prisoners, researchers in Antarctica, shipwreck survivors all describe the slow unraveling of the mind that comes with total loneliness. But they all hold onto the hope of rescue. You have no such hope. There's no one coming to save you. There is no one else, period. Your isolation is eternal. You aren't just in solitary confinement, you are solitary confinement. The entire universe is your cell, and you are its only prisoner. The ultimate horror of stopping time is not that the world stops. It's that you don't. You are forced to keep going, to keep being aware in a silent, static cosmos. It is a unique and perfect hell, tailored for one. The fantasy of stopping time is a tempting one, isn't it? It promises ultimate control, infinite freedom, and a fix for our most human problem: never having enough time. But when you really look at it, when you confront the brutal logic of physics and psychology, the dream collapses into a nightmare. It's a journey from the peak of God-like power to the abyss of absolute solitude. You start as a god and end as a prisoner, trapped not by stone walls, but by the very laws of reality you wanted to control. You're left blind in a world of frozen light, deaf in a universe of suspended sound. But beyond all the physical horror lies the true terror. The crushing loneliness of being the last mind alive. It shows us a fundamental truth. Time isn't a cage we need to escape. It's the river that gives our lives motion and meaning. And sharing our existence, with all its struggles, is infinitely better than an eternity spent as the lonely god of a dead and frozen universe. So, that leaves us with a fun question. If you could press pause, just for 24 hours, before all the terrifying physics kicks in, what is the one thing you would do? Let us know your answer in the comments below. And if you enjoyed this trip into the impossible, make sure to subscribe and hit that notification bell so you don't miss our next What If exploration. Einstein's nightmare: the day the universe froze. Imagine a universe without a future. Not a slow, dying universe, but one where the word next has lost all meaning. A cosmos where every atom, every planet, and every ray of light is frozen in a single, eternal moment. This isn't just a fantasy, it's a scientific nightmare, a scenario that tears apart the very fabric of reality. To understand why, we first have to get our heads around the most profound idea from the mind of Albert Einstein: what time really is. It's a journey that will take us from the simple ticking of a clock to the edge of black holes and the very beginning of everything. And along the way, we'll discover that the steady march of time isn't a given, it's the only thing holding our universe together. What if it happened right now? In this very instant. The thought you're about to have, the next breath you take, the blinking cursor on your screen, all of it just stops. Every particle in the universe, from the photons racing across space to the electrons in your own body, halts in its tracks. A perfect, silent, eternal photograph of a single moment. It might sound like the ultimate superpower, a sci-fi dream come true. But according to the laws of physics, the reality is far more terrifying. This isn't a pause button, it's the complete and utter breakdown of existence. To grasp the sheer scale of this catastrophe, we can't just think of time as something that passes. We have to understand what it is. And for that, we have to go back to a time before Einstein and meet the man who first tried to put time in its place: Isaac Newton. The Clockwork Universe of Isaac Newton. Before Einstein came along and shattered our perceptions, the world ran on a simple, comforting schedule, thanks to Sir Isaac Newton. Back in the 17th century, Newton laid the groundwork for what we now call classical physics. His universe was one of absolute certainty. He imagined space as a giant, unchanging, three-dimensional stage, an infinite container where the cosmic drama plays out. And flowing through this stage was a universal river: absolute time. Newton described this time as something that, of itself, and from its own nature, flows equably without regard to anything external. Think about that. He was saying that somewhere out there, a master clock for the entire universe is ticking away at a perfectly steady rhythm, completely separate from everything else. It didn't matter if you were sitting on a park bench, riding a horse, or flying in a spaceship, this one true time was the same for everyone, everywhere. The time in London was the same as the time on Jupiter. It was the ultimate metronome, setting the beat for all existence. Our everyday clocks, Newton said, were just imperfect copies. They measured what he called relative time. the duration of things we can see, like the spin of the Earth or the swing of a pendulum. But underneath it all was that absolute, mathematical, and ultimately invisible flow. For over 200 years, this idea of a clockwork universe reigned supreme. It was elegant, it made sense, and it worked perfectly for describing the world. We could see apples falling from trees, planets orbiting the sun. Space was the static background, and time was the relentless, universal drumbeat. But this tidy picture had a crack in its foundation, a problem that got bigger as we studied one of the universe's most fundamental components: light. The laws of physics, it turned out, were about to get a whole lot weirder. And it would take a young patent clerk in Bern, Switzerland, to see that the universal clock was an illusion. The stage and the river weren't separate at all. They were one and the same. Einstein's revolution. The taffy of time. At the turn of the 20th century, physics was in crisis. Experiments had revealed something deeply strange about the speed of light. It was constant. Now, that sounds simple, but the implications will break your brain. Imagine you're in a car going 50 miles per hour, and you turn on your headlights. You'd expect the light to travel at its own speed plus the 50 miles per hour of your car. But it doesn't. Someone standing on the sidewalk and you in the car will both measure the speed of that light as exactly the same. About 671 million miles per hour. This completely broke Newton's rules. How could speed be absolute when motion was supposed to be relative? In 1905, Albert Einstein, in his theory of special relativity, came up with a wild solution. He said, what if the speed of light is the one true constant? What if it's the absolute thing, and everything else, including space and time, has to stretch and shrink to accommodate it? This was the start of his revolution. From that one idea, the clockwork universe began to fall apart. Einstein realized that if the speed of light is always the same for everyone, then something else has to change. That something was Newton's absolute time. He showed that time isn't a universal river. It's more like a personal stream. The rate that time flows for you depends on how fast you're moving. This is the famous idea of asterisk time dilation. Here's how to picture it. Imagine a light clock where a single particle of light, a photon, bounces between two mirrors. Each time the photon hits a mirror, the clock ticks. If that clock is just sitting there, the photon travels a short, straight path up and down. Tick, tock. But what happens if you put that clock on a high-speed train? From your view on the platform, the clock is moving. So as the photon travels up, the top mirror has moved forward. The photon now has to travel a longer, diagonal path to catch up. Since the speed of light can't change, and the photon is now traveling a longer distance for each tick, it simply takes more time to complete a tick. From your perspective, the moving clock is running slower than your own. It's not an illusion. Time itself is flowing more slowly for that clock. This effect is tiny at everyday speeds, but as you get closer to the speed of light, it becomes huge. For an astronaut at 99.9% of the speed of light, years could pass on Earth while they experience only months. And this isn't just a theory. You use it every day. The satellites in our GPS network are orbiting Earth at thousands of miles per hour. Their clocks run a tiny bit slower than ours on the ground because of their speed. They also run a bit faster because of weaker gravity, but we'll get to that. Physicists have to correct for these relativistic effects. If they didn't, your GPS would be off by several miles every single day. And it gets weirder. If time can stretch, space can shrink. Einstein also showed that for a moving object, its length in the direction of motion gets compressed. This is asterisk length contraction. That spaceship going at 99.9% of the speed of light wouldn't just experience slower time. To an outside observer, it would look physically shorter. This was the first hint of an even deeper truth. Einstein had shown that motion affects time, and motion affects space. The two weren't separate. They were intimately connected. He had set the stage for his greatest masterpiece, a new vision of reality where space and time were a single, four-dimensional fabric. Weaving the fabric. Spacetime explained. For 10 years after special relativity, Einstein wrestled with a big problem: gravity. His theory worked perfectly for things moving at a constant speed, but it didn't include acceleration or the force that runs the cosmos. His quest to include gravity led him to an idea so profound it would completely redefine our universe. In 1915, he gave us his theory of general relativity. The idea starts with a powerful leap of imagination. We're used to thinking in three spatial dimensions: length, width, and height. Einstein's big move, building on the work of his former teacher Hermann Minkowski, was to treat time as a fourth dimension. Not as a separate idea, but as a physical dimension just as real as the other three. This four-dimensional reality is what we call asterisk spacetime. Every event, from a star exploding to you sipping your coffee, has a unique address in spacetime, its location in space, and its moment in time. Einstein had already shown that moving through space affects how you move through time. Now, he would show how this unified fabric could explain gravity itself. This brings us to the most famous analogy in all of physics: the bowling ball on a trampoline. Imagine space-time as a flat, stretched-out rubber sheet. With no matter or energy, space-time is flat. A marble rolled across it travels in a straight line. But what happens when you place a massive object, like a bowling ball, on the sheet? It creates a curve, a deep dip in the fabric. Now, if you roll that marble near the bowling ball, it doesn't travel in a straight line anymore. It follows the curve, spiraling inward. From a distance, it looks like the bowling ball is using some mysterious force to pull the marble in. But from the marble's point of view, it's just following the straightest possible path through a curved space. This, Einstein said, is gravity. Gravity isn't a force that pulls. It's the shape of spacetime itself. The sun doesn't pull the Earth through space. The sun's enormous mass warps the spacetime around it, creating a deep gravity well. The Earth, in its orbit, is just following the straightest possible path, a geodesic, through that curved 4D landscape. Your chair isn't pushing up on you to fight gravity's force. It's stopping you from following your natural path through curved spacetime toward the center of the Earth. It's a mind-bending concept. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. It's a cosmic dance. And it wasn't just a pretty idea, it made testable predictions that were different from Newton's. One of the first proofs came from Mercury's weird orbit. For decades, astronomers were puzzled by a tiny wobble in Mercury's orbit that Newton's laws couldn't explain. But when Einstein applied his equations, he found that the extreme curvature of spacetime so close to the Sun perfectly accounted for it. Another spectacular proof came in 1919 during a solar eclipse. Einstein's theory predicted that the Sun's gravity would bend the light from distant stars as it passed by. By watching the stars during the eclipse, astronomers saw that their apparent positions shifted. Spacetime was being warped, just as Einstein predicted. General relativity has become one of the most rigorously tested theories ever. From gravitational lensing, where entire galaxies bend light, to the detection of gravitational waves, which are literal ripples in the fabric of spacetime, Einstein's vision of a dynamic universe has been proven right again and again. So now our picture of time is much deeper and stranger. It's not a universal clock. It's a dimension, woven together with space to form a fabric that can be stretched, shrunk, and curved. But this leads to an even more basic question. Why does it flow at all? And why does it only seem to flow in one direction? The arrow of time. Why tomorrow is never yesterday. We take it for granted that time has a direction. We remember the past, but not the future. An egg can be scrambled, but it will never unscramble itself. This one-way street is what physicists call the asterisk arrow of time. But here's the puzzle. At the most fundamental level, the laws of physics don't really care about the direction of time. They're almost perfectly time-symmetric. A video of two billiard balls colliding looks just as real if you play it backward. So if the basic laws have no preference for past or future, where does this relentless forward march come from? The answer, it turns out, comes not from gravity or relativity, but from the science of heat and disorder. Thermodynamics. Specifically, it comes from the second law of thermodynamics. This law introduces a concept called entropy, which is basically a measure of disorder or randomness. And the law states that in a closed system, the total entropy, or disorder, will always tend to increase over time. Let's break that down. Imagine a neat pyramid of blocks. This is a low entropy state, it's highly ordered. There are very few ways the blocks can be arranged to make a perfect pyramid. Now, imagine an earthquake shakes the table. The pyramid falls into a messy, random pile. This is a high entropy state, it's disordered. There are vastly more ways for the blocks to be arranged in a messy pile than in a perfect pyramid. The universe naturally moves from order to disorder, simply because there are overwhelmingly more ways to be disordered. A random pile of blocks will never spontaneously build itself into a perfect pyramid. This tendency towards increasing disorder is what gives time its arrow. The universe as a whole is moving from a state of incredible order to a state of increasing disorder. The reason we experience time moving forward is that our universe started in a very special, low entropy condition. At the Big Bang, the universe was unbelievably hot and dense, but it was also exquisitely uniform and ordered. Ever since, it's been expanding, cooling, and getting more disordered. Stars burn their fuel and radiate heat. Galaxies drift apart. This constant increase in the universe's total entropy is the engine that drives time forward. Think of a drop of ink in a glass of water. At first, you have an ordered state. Ink here, water there. As time moves forward, the ink spreads out until the water is a uniform, murky gray. That's a high entropy state. You'll never see the murky water separate back into a clear liquid and a single drop of ink. The forward direction of time is the direction of the ink spreading out. This connection is fundamental. The processes that define our lives, aging, remembering, even thinking, are all processes that increase the total entropy of the universe. Causality itself, the idea that a cause comes before an effect, is tied to this. Dropping a glass causes it to shatter because the shattered state has much higher entropy. The reverse is so statistically impossible it just doesn't happen. So, time isn't just a dimension. Its direction, its flow, is a consequence of the universe's unstoppable march toward chaos. The past is the ordered state. The future is the disordered one. Now, with this complete picture, we can finally face the nightmare. What happens if you try to stop it? What happens on the day the universe freezes? The nightmare scenario. The day the universe froze. Let's go back to our terrifying idea. In a single instant, the arrow of time is broken. The fourth dimension is gone. What would that be like? Science fiction often shows a hero moving freely through a frozen world. But the physical reality is infinitely more catastrophic. First, let's pretend, like in the stories, that you are somehow immune. Time has stopped for everything else. What do you experience first? Absolute and total sensory deprivation. You'd be plunged into darkness. You see because photons, particles of light, travel from a light source, bounce off things, and hit your eyes. If time is stopped, those photons are frozen in place. The photon that was an inch from your eye will stay there forever. No new light can reach you. The world wouldn't just be dark. It would be the complete absence of light. Then, the silence. Sound travels as waves of vibrating molecules in the air. If time stops, all molecular motion stops. The air around you would become a rigid, unmoving crystal. No vibrations, no sound. An eternal, crushing silence. But you wouldn't be around to worry about it for long, because you couldn't move or even think. To take a single step, you'd have to push air molecules out of the way. But those molecules are now frozen in spacetime, as solid and immovable as a wall of diamond. You'd be instantly trapped. Even if you could move, you couldn't breathe. That requires moving air into your lungs. Impossible. But it's even more fundamental. The biological processes that make you happen over time. Your heart beats, blood flows, neurons fire. If the atoms that make up your body are frozen, you wouldn't just die. You would cease to exist in any meaningful way. The very act of thinking, a stream of electrochemical signals, would be impossible. Your consciousness would be a frozen puddle. Now let's push past the personal annihilation. What happens to reality itself in a timeless universe? It just breaks. All motion is a change in position over time. If time is zero, velocity is zero. Kinetic energy vanishes. Every planet, every star, every galaxy would halt instantly. But they wouldn't just hang there. Gravity, as Einstein showed us, is the curvature of spacetime. What happens to gravity when you remove one of the four dimensions? The equations of general relativity simply fall apart. The concept becomes nonsensical. Cause and effect, the bedrock of reality, would be gone. An effect follows a cause because time moves forward. Without a before and after, the entire logical structure of the universe vanishes. The ultimate paradox is this. If time truly stopped, nothing could happen. The word itself implies a transition between states, which requires time. To even observe a timeless universe is a contradiction, because observation is a process. It's a state of pure non-being. It is Einstein's ultimate nightmare. An equation where the t for time is set to zero, and the entire structure of physics collapses. The nightmare of a frozen universe isn't just things standing still. It's the erasure of the laws that allow things to be at all. It's the end of motion, energy, light, thought, and causality. It is the ultimate cosmic shutdown. Thinking about these cosmic what-ifs really stretches our understanding of reality. The laws of physics aren't just equations, they're the rules that write the story of our universe. If you enjoy having your mind bent by the biggest questions in science, make sure you subscribe. We've got plenty more journeys into the weird and wonderful cosmos to take together. So, we're back from the edge of a timeless abyss, back to our world where clocks tick and the future is still on its way. This thought experiment, while a physical impossibility, serves a purpose. It stress tests reality, showing just how critical this dimension we take for granted really is. We've seen that time isn't the simple metronome Newton imagined, but a dynamic part of the universe itself, woven into the fabric of spacetime. We've learned that its forward direction isn't a given, but is driven by the universe's relentless march from order to chaos. Time is the dimension of change. It's what allows for motion, energy, cause, and effect. It is the canvas on which the laws of physics paint the story of the cosmos. Far from being a cage that locks us into a one-way trip, the flow of time is what makes a trip possible in the first place. Einstein's nightmare of a frozen universe reveals a beautiful truth. The seemingly restrictive laws of physics, the constant speed of light, the arrow of time are not limitations. They are the very pillars that hold up reality. They are what allow for a universe that can build stars, form galaxies, and give rise to beings capable of looking at the sky and wondering, what is time? The fact that the universe has a future is the greatest gift of its fundamental laws. The clock is ticking. And that is a very, very good thing. Science just explained the end of time. What if the ultimate end isn't a bang? Or a whimper? But a complete stop? Imagine you're the only person in the universe who can still move. For a moment, it feels like a superpower. You are a god in a silent, static kingdom. A living mind in a monument to a single, frozen instant. But then, the terrifying truth dawns on you. You can't see. You can't breathe. You can't even move. Science might have just explained why the end of time wouldn't be a grand spectacle, but a silent, invisible prison. And the reason is genuinely mind-bending. We've all wondered about how the universe will end. We picture these cataclysmic explosions, or maybe a slow, fading ember in an infinite night. But all of those scenarios, as grand as they are, still have one thing in common. They happen over time. They're a sequence of events. But what if the very idea of sequence, the foundation of cause and effect, just stops? What if the movie of the universe doesn't fade to black, but the projector just jams on a single frame for all eternity? This isn't some philosophical daydream, either. This is a question that pushes physics to its absolute limits, forcing us to ask what time, reality, and even our own consciousness are really made of. The journey to the answer starts with one single, impossible moment. A moment where everything stops. The frozen moment. Picture it. I mean, really picture it. You're in the middle of a bustling city square. The symphony of life is at full volume. A flock of pigeons has just taken off, their wings caught in a dozen different angles. A street musician is mid-strum, fingers pressed on guitar strings that are now perfectly still. A kid's laugh is frozen on their face, a perfect sculpture of joy. 1,000 conversations have been halted mid-syllable. A fountain's spray hangs in the air like a chandelier of motionless crystal. For the first fraction of a second, you don't even notice. Your brain's still catching up, processing the last bit of motion. But then, the silence hits you. And it's not just quiet. It's a fundamental absence of sound. It's a pressure in your ears, a void so deep it feels physical. The hum of traffic, the distant siren, the murmur of the crowd all gone. The air itself has gone silent. You look around, your heart starting to pound against your ribs. The scene is surreal, like a perfect 3D photograph. The pigeon with its wings out isn't falling. The laughing child isn't moving. The water droplets aren't giving in to gravity. Everything is locked in absolute, perfect stillness. For a second, a thrilling thought hits you. I'm the only one who can move. You're the master of this frozen world. You can walk among these statues of life, an unseen ghost. You take a step, a confident, powerful stride into your new kingdom. And that's when the second horror hits you. The world vanishes. You're plunged into a blackness more complete than any cave, more absolute than the deepest ocean. It's a sudden, total, terrifying blindness. The sun is still in the sky, the streetlights are still on, but you see nothing. The light is still there, right? The countless trillions of photons that paint our world are still filling the space around you. But that's the problem. They are asterisk still. For you to see anything, a photon has to travel from an object to your eye. It has to hit your retina and get converted into an electrical signal for your brain. But in a world where time has stopped, photons are frozen mid-flight. They hang motionless in the air like a cloud of invisible dust. They're no longer messengers traveling at nearly 300,000 kilometers per second. They're just static, suspended, unable to finish their journey. The light from the sun is trapped a few feet from its surface. The light from that street lamp is a motionless haze around the bulb. The universe is full of light, but all you perceive is an infinite, suffocating darkness. You're blind. So, you're deaf. And you're blind. Panic starts to creep in. You try to scream, to prove to yourself that you still exist. You open your mouth, force air from your lungs. And nothing happens. Sound, just like light, needs time to travel. It's a wave of pressure, molecules vibrating and passing energy to the next. In a world where time is stopped, the air molecules aren't vibrating. They can't pass along the message of your scream. It dies in your throat, a silent intention. The darkness is absolute. The silence is unbroken. And that's when you discover the final, inescapable truth of this new reality. You're in a prison. The invisible prison. You try to take another step, a frantic one this time, desperate to escape this sensory deprivation chamber the universe has become. Your foot won't move. You push, you strain, every muscle screaming with effort. It feels like you're pushing against a wall of solid diamond. But there's nothing there. Except. There is something there. It's the air. The air you used to walk through without a second thought is now your cage. See, what we call temperature is really just the motion of atoms and molecules. The warmer something is, the faster its particles are zipping around. But when time stops, all motion stops. Every atom in the universe stops vibrating. This isn't just cooling down, it's the instantaneous arrival at absolute zero. That's a temperature colder than deep space, a state physicists think is impossible to actually reach, because it would take an infinite amount of energy to get there. But in our scenario, here it is. The molecules of air are no longer a gas. With all their energy gone, they're locked into a perfectly rigid, invisible, solid structure. You are encased in a block of frozen nitrogen and oxygen. You can't move a single millimeter, because that would mean displacing trillions upon trillions of immovable particles. You are trapped. But the prison is even smaller than you think. It's not just the air around you. It's the air inside you. The oxygen in your lungs is now a solid. You can't breathe. Your diaphragm can't move, and you can't expel the solid air already in your lungs. The terror deepens as you realize this goes all the way down. Your own body is a symphony of motion. Your heart beats. Your thoughts are electrical signals, ions moving across membranes in your brain. Your very consciousness is a process. It's a constant cascade of chemical reactions. All of it requires time. Without time, no chemical bonds can form or break. No nerve can fire. The you that was supposed to be a god in this frozen world is a paradox. To be a conscious observer requires the very thing that's been taken away. This is the ultimate horror of stopped time. It's not a world you can explore. You wouldn't be a god or a ghost. You wouldn't be anything. You would be just as frozen, just as static, and just as unaware as the rest of the universe. And that brings us to the truly mind-bending part. If time stopped for everything, including the processes of your own perception, how would you know? You wouldn't. The stop would be completely and utterly invisible. Okay, before we get into the actual science of how the universe is really supposed to end, just take a moment. The fact that you can even think about this idea that your neurons are firing, that light is traveling from this screen to your eyes, that time is flowing is kind of a small miracle. If you appreciate journeys like this into the biggest questions out there, take a second to subscribe and join us. Every new explorer helps us go deeper. Now, let's look at the real physics of the end of time. The science of a timeless universe. Okay, so a sudden, universal stop makes for a great horror story, but it's not how physics actually predicts the end will come. Science points to something far slower, more creeping, and even more final: the heat death of the universe. It's also called the Big Freeze, and it's the most widely accepted theory for our ultimate fate, based on one of the most solid laws of nature. To get the heat death, you first need to understand the second law of thermodynamics. It's a rule that governs everything from your coffee getting cold to the fate of the cosmos. It basically says that in a closed-off system like our whole universe, disorder, or entropy, always tends to increase. Think of it this way. You build a perfectly ordered sandcastle on the beach. That's a low entropy state. It's structured and complex. Now, the wind and the waves will inevitably break that castle down, scattering the sand grains randomly. That's a high entropy state. It's disordered, simple, and way more likely. There are way more ways for sand to be a random pile than for it to be a castle. Believe it or not, the universe began in a state of incredibly low entropy. The Big Bang wasn't chaos. It was a moment of immense order, with everything packed into a hot, dense state. That low entropy starting point is like a wound-up clock that's been ticking down ever since, giving time its forward direction. The arrow of time is tied to this constant march from order to disorder. Every single thing that happens adds to this disorder. Every star that burns, every galaxy that forms, even every thought you have, is part of this cosmic unwinding. They take useful, ordered energy and turn it into useless, disordered waste heat. A star is an ordered ball of gas that releases energy, but in doing so, it increases the total disorder of the universe. So, what happens when this process plays out to its absolute end? That's the heat death. Fast forward through unimaginable amounts of time. Billions of years from now, the universe's expansion will have pushed all other galaxies so far away they'll be invisible. The night sky will be empty. A trillion years from now, there won't be any new stars. The universe will run out of gas. The last remaining stars will flicker and die, leaving behind cold, dead husks. The universe becomes a graveyard of stellar corpses and black holes, drifting through an expanding, cooling darkness. But it doesn't even end there. Over timescales that just break our brains, we're talking a Google years. That's a 1 with 100 zeros after it. Even these last holdouts of matter will give up. Stephen Hawking was the one who predicted that black holes aren't forever. Through a process we now call Hawking radiation, they slowly evaporate, leaking their energy back into the universe as a faint fizz of particles. Even the protons that make up matter itself might eventually decay, though that's still a theoretical idea. So what's left? A universe that has reached maximum entropy. A vast, dark, and freezing void, filled with a thin, uniform soup of stray particles. In this state, energy is perfectly spread out. There are no hot spots, no cold spots. No stars, no planets, no structure. And if there's no temperature difference, energy can't flow. If energy can't flow, nothing can happen. Ever again. This is the asterisk true, end of time. Not because time has paradoxically stopped, but because change itself has become impossible. Time becomes meaningless when every moment is identical to the last. The cosmic story will be over. But this whole bleak picture is built on our current understanding of time. What if that understanding is wrong? What if time isn't the fundamental river we think it is? Some of the weirdest areas of physics are asking that exact question. Some theories trying to connect the dots, like loop quantum gravity, suggest something way stranger. They propose that spacetime isn't a smooth, continuous fabric. Instead, it's made of discrete, indivisible chunks like pixels on a screen. And at that tiny, fundamental level, the concept of time might not even exist. In this view, time isn't fundamental. It's an asterisk emergent property. Think of it like the temperature of a gas. A single gas molecule doesn't have a temperature. That property only emerges from the behavior of trillions of molecules bumping into each other. In the same way, time might just be an effect that emerges from the changing relationships between things in the universe. And that leads to the most unsettling idea of all: the invisible event. Let's go back to our thought experiment. The universe freezing in a single instant. We figured out that if you were part of the freeze, you'd never know it, since your consciousness would stop too. Now, let's take that one step further. What if, a moment later or a billion years later, it wouldn't matter, time started again? From your point of view, as a character inside this cosmic movie, what would you feel? Absolutely nothing. There'd be no jolt, no weird feeling of lost time, no gap. You'd be in one moment, and then the very next, with zero awareness that an eternity of frozen stillness might have passed in between. For the characters in a movie that's been paused and unpaused, the story is perfectly continuous. No time has passed for them. And that's the core of this invisible event. If time is just something that emerges from how the universe works, not a fundamental thing that exists on its own, then a universal pause isn't just impossible to see from the inside. The idea itself is physically meaningless. It's like asking what's north of the North Pole. The question doesn't even make sense in that context. Physics has a hard time even defining what a universal stop would mean. Time is so tangled up with space, motion, and causality that you can't just pull it out without everything collapsing into paradox. So, the scientific end, the heat death, isn't a stop. It's the end of change. But the philosophical question that comes out of our little horror story is a chilling one. If it were possible for the universe to stop and restart without anyone inside noticing, how could we ever know it hasn't already happened? How do you know that time didn't stop a second ago, for a trillion years, and just restart right now? You don't. There's no experiment you could run, no observation you could make, that could ever tell you. Our experience of a smooth, continuous flow of time might just be an illusion, a feature of our consciousness, not a fundamental property of reality. So where does that leave us? We started with a simple, terrifying question: what if time just stops? We went from that idea of a superpower to an invisible prison. Then we saw how the real laws of physics point not to a sudden stop, but to a slow, cold fade to black, the heat death, where the universe just runs out of steam. The end of the universe, according to science, isn't an event we can watch. It's the gradual end of all events. It's a slow descent into an eternal, silent equilibrium, where time becomes irrelevant because nothing happens to mark its passage. The cosmos won't end with a bang or a whimper, but with an endless, featureless silence. And yet, the deeper we look at time itself, the weirder it gets. The possibility that time is just an emergent property of a deeper, timeless reality leaves us with a dizzying, unanswerable question. We're observers trapped inside the system, our perception of reality tied to the very flow we're trying to understand. The hypothetical stop would be an event so total it would erase itself from existence. So, we're left here, in the now. In this brief, warm, and ridiculously improbable moment of cosmic history where the universe is still wound up, where stars are shining, and where collections of atoms can, for a little while, think about their own existence. The clock is ticking down, and entropy is always increasing. But for now, the movie is still playing. And we're unbelievably lucky to be here to watch it. The final question, then, is for you. If time could stop and restart without us ever knowing, what does that say about the continuity of your own consciousness? Let me know what you think in the comments. Scientists explain why light dies when time stops. If time stopped, right now, this is what you'd see. Nothing. Instantly, your world would go black. Every star in the sky, the screen in front of you, the memory of a face. All of it extinguished. You'd be plunged into a darkness deeper than any cave and a silence more profound than the vacuum of space. But why? Why would light, the fastest thing in the universe, just die the moment time did? This isn't a question for philosophy. It's a question of physics. The answer is woven into the most fundamental rules of our reality by Albert Einstein himself. To get it, we don't just have to imagine stopping a clock. We have to imagine hitting the cosmic pause button on the entire universe. And when we do that, as we're about to see, the fantasy of controlling time dissolves into a scientific nightmare. You wouldn't be the master of the universe. You'd be its only victim, trapped in a silent, lightless, and utterly immovable prison. The journey to understanding why is a detective story, and it starts with a simple observation that unravels the very nature of existence. We'll figure out why movement becomes impossible, why your own thoughts would just stop, and why the death of time means the instantaneous death of every single photon that paints our reality. Stick around. This gets weird, but the payoff will change how you see the universe and the light within it forever. The immediate nightmare. A world frozen solid. Alright, let's do it. Let's press the button. In this thought experiment, you and only you get a single magical exemption. For one eternal second, the universal clock stops for everything but your consciousness. You are a lone observer in a frozen sea of moments. What happens first? The first thing you'd experience is that sudden, terrifying plunge into absolute, total blackness. This isn't like a power outage, where your eyes adjust to the faint glow of the moon. This is a complete absence of light. See, sight works because particles of light, called photons, travel from a source, a star, a light bulb, bounce off stuff, and then zip into your eyes. Your brain takes a lifetime of these photon detections and turns it into a picture of the world. But if time is frozen, every single photon in the universe stops dead in its tracks. Think about that. The light that left the sun 8 minutes ago is now locked in place, millions of kilometers away. The photons carrying this sentence to your eyes are frozen in the air between the screen and your face. No new light can reach you. The universe hasn't gone dark because the lights went out. It's gone dark because the very idea of travel for light has ceased to exist. You would see nothing. A profound, absolute nothing. At the same instant, you'd be hit by a silence more complete than any soundproof chamber on Earth. Sound is just a vibration, a pressure wave moving through a medium like air. Those waves make your eardrums vibrate, sending signals your brain calls sound. With time stopped, motion is impossible. The air molecules that were carrying the hum of your computer or the sound of your own breathing are now petrified mid-vibration. No vibration can travel, so no sound can be heard. But the horror is just getting started. You'd quickly realize the darkness and silence are the least of your problems. You are trapped. Utterly. Try to move your arm. You can't. The air around you, which feels like nothing, is actually a chaotic swarm of trillions of nitrogen and oxygen molecules zipping around at hundreds of miles per hour. We move through it because the molecules just get pushed out of the way. But in a timeless world, every one of those molecules is locked into a fixed position. The atmosphere has become an invisible, immovable, perfectly rigid wall. Trying to push your hand through it would be like trying to punch through solid diamond. You are held in place by the very air you were just breathing. And that brings us to the final problem. You can't breathe. Breathing is mechanical. Your diaphragm contracts, creating low pressure in your chest, and outside air rushes in. But now, nothing can rush anywhere. The air molecules are frozen. You couldn't even expand your chest against the rigid air around you, and even if you could, no new oxygen could flow into your lungs. Even more fundamentally, your own body would betray you. Thinking, feeling, seeing. These are all complex chains of biochemical reactions. For a neuron to fire, ions have to pass through a membrane. For a muscle to contract, molecules have to be metabolized. For your brain to even process anything, chemical signals have to move. All of these processes, every single one, require change over time. Without time, there is no change. Your last thought would hang, unfinished, in the frozen circuits of your brain. You'd be a ghost trapped in a photograph. A mind adrift in a perfectly silent, perfectly dark, perfectly still universe. But why? To find the answer, we have to become cosmic detectives and look for clues at the scene of a famous scientific crime, an experiment that failed so spectacularly it changed the world. The cosmic crime scene and the first clue. To solve the mystery of why light dies when time stops, we first have to understand what it is. For most of the 19th century, physicists were pretty sure they had it figured out. Light was an electromagnetic wave. And like all waves, they knew sound in air, ripples on a pond. It needed something to travel through. An ocean needs water, sound needs air, so they figured light must need some invisible substance to ripple through the vacuum of space. They called it the luminiferous ether. They imagined it was a motionless, invisible grid filling all of space, and that Earth must be moving through it. This led to a very clear prediction. There should be an ether wind. Think of it like driving a convertible on a windless day. As you speed up, you feel a breeze on your face. That's the air rushing past you. So, as the Earth plows through this stationary ether, we should feel an ether wind. Send a beam of light into this wind, and it should slow down. Send it with the wind, and it should speed up, just like a boat on a river. The speed of light, they thought, should depend on which way you were looking. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to detect it. They built an incredibly clever device that split a beam of light, sent the two halves on perpendicular journeys of the same length, and then brought them back together. Imagine two identical swimmers racing in a river. One swims across the current and back, while the other swims downstream and then back upstream. Even if the distances are identical, the swimmer fighting the current will always take longer. Michelson and Morley expected the two light beams to arrive back at slightly different times, creating a telltale pattern. They set up their massive stone slab, floating it on Mercury for stability, and looked. And they saw nothing. No difference at all. They rotated it. They tried again at different times of the year, when the Earth was moving in a different direction. Still nothing. The light beams always arrived at the exact same time. This wasn't a failure of the experiment worked perfectly. The shocking part was the result. It was a finding so profoundly weird that it took a young patent clerk in Switzerland to figure out what it really meant. The result of the Michelson-Morley experiment could only mean one thing. The speed of light is not relative. It's absolute. It doesn't matter if you're standing still or flying in a spaceship at half the speed of light. If you measure the light coming towards you, you will always get the exact same number. About 300,000 kilometers per second. This is our first, crucial clue. It's the law that modern physics is built on, and it's the key that unlocks the whole mystery. Building the ultimate clock. The fixed speed of light isn't just a weird fact, it's a law of the universe. And when a law is that absolute, you can use it to build a perfect clock. Not one made of gears, but one made of light itself. Imagine two mirrors facing each other, a fixed distance apart, let's say 150,000 kilometers. We release a single photon from the bottom mirror. It travels up, hits the top mirror, and reflects back down. Tick. The photon is back where it started. How long did that take? Light travels at 300,000 kilometers per second. Our photon went 150,000 km up and 150,000 km down, a total of 300,000 km. So, one tick of our light clock takes exactly 1 second. It's the ultimate timekeeper, governed by a universal constant. Now, let's put our clock on a transparent, super-fast spaceship flying past you. For someone on the ship, nothing changes. The clock is right next to them. The photon just goes straight up and straight down. Tick, tock, 1 second at a time. But you're not on the spaceship. You're watching it zoom by. And from your perspective, something very strange happens. You see the photon get released. But while it's traveling to the top mirror, the clock itself has moved to the right. So from your point of view, the photon doesn't go straight up. It travels on a diagonal. It hits the top mirror, and on its way back down, the clock keeps moving. So the return journey is also a diagonal, forming a V shape. This is the critical moment. For the person on the ship, the photon travels a short, straight path. For you on the ground, it travels a much longer, diagonal path. We both agree. The path you saw is longer. Now, remember our first clue. The speed of light is the same for everyone. The person on the ship sees the photon moving at speed c. You on the ground also see that same photon moving at speed c. This is where reality starts to bend. From your perspective, the photon traveled a longer distance, but at the exact same speed. The only possible conclusion? It must have taken more time. From your point of view, the tick of the moving clock takes longer than 1 second. The clock on the spaceship is running slow. This isn't an illusion. It's a fundamental consequence of our universe called time dilation. And it's real. Clocks on fast-moving GPS satellites run slightly slower than clocks on Earth. If we didn't constantly correct for this, the tiny time difference would accumulate, causing GPS navigation to fail with errors of a few kilometers every single day. Astronauts on the ISS age just a fraction of a second slower than we do. A moving clock runs slow, and time itself is tangled up with the speed of light. The slowdown and the breaking point. So, the faster something moves through space, the slower it moves through time. Let's push that idea to its limit. Imagine our spaceship is now flying past at 90% of the speed of light. From your perspective, that V-shaped path the photon takes is now incredibly wide and stretched out. The distance it has to cover for a single tick is more than double the original. The result? For every 1 second that ticks by for the passenger, you on the ground would measure about 2-3 seconds passing. The passenger is now aging less than half as fast as you are. Let's get even more extreme. 9,999% of the speed of light. The photon's path is now a phenomenally long, shallow triangle. The slowdown is immense. A passenger takes a 10-year round trip to a nearby star. When they return, for you on Earth, 7,000 years would have passed. Throughout all this, the passenger feels nothing strange. Their heart beats normally, their clock still ticks once per second. The slowdown is only visible to an outside observer. Now for the final step. What happens if the spaceship reaches 100% of the speed of light? As we get closer and closer to *C*, that tick of the light clock, from our perspective, slows towards infinity. The diagonal path becomes so stretched out that it's basically two parallel horizontal lines. For a tick to complete, the photon would have to travel an infinite distance. A tick that takes an infinite amount of time is a tick that never happens. From the perspective of a stationary observer, at the speed of light, time stops. And this brings us to light itself. Photons don't approach the speed of light, they're born traveling at it. They only exist at light speed. This leads to a mind-shattering truth. Photons do not experience time. Now, we have to be careful here. Physically, there's no such thing as a photon's perspective. You can't ride along with one. But as a thought experiment, it reveals something profound. From the moment a photon is emitted from a star 13 billion light years away to the moment it enters your eye, for that photon, zero time has passed. Its emission and its absorption happen in the same instant. For a photon, there is no journey. There is only arrival. This is our final clue. A photon is a particle that exists in a state where time doesn't flow. So what happens if we put this timeless particle into a timeless universe? The grand conclusion. The universe goes dark. We've followed the clues. The Michelson-Morley experiment gave us the absolute speed of light. The light clock showed us that time is relative and slows with motion. And pushing that to its limit, we found that at light speed, time stops, which is the natural state for a photon itself. Now we can answer the question. Why does light die when time stops? The answer is that motion is, fundamentally, change over time. Speed is distance divided by time. If the time part of that equation becomes zero, the whole concept of speed falls apart. For us, here in the flow of time, we can watch a photon travel from A to B and measure how long it took. Our experience of time is what allows the photon's motion to have any meaning. Time is the river. The photon is the boat. If the river stops flowing, what happens to the boat? If the universal clock stops, the very medium that allows for change is gone. For a photon, whose entire existence is defined by its unstoppable motion, this is a physical paradox. A photon is motion. A stationary photon is an impossibility. When time stops, the engine of light's existence is switched off. Every photon in the universe would cease its journey. Its velocity would become zero because the temporal dimension it needs to move through is gone. They'd be frozen in place like flies in amber. This is why your world goes black. The light from your lamp would be suspended motionless in the air. The light from the sun would be frozen in the vacuum of space. The ancient light from distant galaxies would halt in the intergalactic void, an invisible ghost. But it's even more profound than that. Even if a photon was already inside your eyeball when time stopped, you still wouldn't see it. Vision isn't passive. It's an active process that takes time. When a photon hits a cell in your retina, it triggers a chemical reaction, which creates an electrical signal that travels along your optic nerve to your brain, a journey that also takes time. If time is frozen, that entire process is impossible. The nerve can't fire. The brain can't process. The information of the photon's arrival could never be created or transmitted. The hardware of the universe, the movement of light, and the software of your biology, the process of vision, both crash at the same time. The flow of time isn't a prison. It's the canvas upon which reality is painted. It's what allows for change, for motion, and for the existence of light. Without the river of time, the universe becomes a single, static photograph, and every star is extinguished in an instant. So, the power to stop time isn't a superpower. It's a collision with the laws of physics. It wouldn't grant you freedom. It would throw you into a sensory deprivation tank the size of the universe. We followed the clues, from a brilliant 19th century experiment that revealed a cosmic speed limit, to Einstein's thought experiments that showed how fluid time really is. We saw how time stretches for objects in motion, and how for a particle of light, it stops altogether. And that was the key. Light doesn't just travel through time. Its ability to travel at all is granted by the flow of time. Photons are timeless travelers, but they need a temporal landscape to cross. When that landscape vanishes, so does their journey. The world goes dark not because the light is gone, but because it's trapped. The next time you look up at the night sky, at stars whose light has traveled for centuries to reach you, you're not just seeing distant suns. You're seeing evidence of the profound and unbreakable marriage of light and time. You are seeing a universe in motion, a universe that is allowed to change, to evolve, and crucially to be seen. The steady march of time can feel like a limitation. But it's not. The flow of time is the very thing that makes existence possible. It is the current that carries the light, the silent engine that paints the cosmos, allowing this incredible universe to unfold, one moment at a time. Without it, there's only darkness. The day the universe froze solid, in a single instant, it's over. Not with a bang, but with a quiet, sudden stop. Every planet in its orbit, every star in its fiery dance, every particle in the cosmos just freezes. An unseen force has hit the pause button on reality, and time itself has stopped. Welcome to the day the universe became a silent, breathtaking diorama. This isn't a story about things slowing down, or a moment of peace. It's about the complete and utter stop of all change. A universal, instantaneous halt. What would that even look like? What would it feel like? And what could it possibly tell us about the fundamental nature of reality itself? To figure this out, we have to take a journey from the most intimate, human scale to the mind-bending edges of the cosmos. We'll explore what gravity really is, not a force, but the actual shape of reality, and then see what happens when that reality gets locked in place. We'll watch orbits freeze and galaxies hang like chandeliers in an eternal twilight. The story of how everything stops is, weirdly enough, the story of how everything truly is. The personal freeze. Imagine you're sitting in a quiet room with a cup of coffee. You lift it, and a single, dark drop falls from the rim. You watch it descend, a tiny world ruled by gravity and the simple passing of moments. And then, it doesn't land. It just hangs there, suspended. A perfect, glistening sphere of liquid, a millimeter from the table. You try to blink, but your eyelids won't move. You try to take a breath, but the air in your lungs is static. The command from your brain to your muscles, a cascade of electrical signals, is frozen halfway there. There is no sound. The vibrations of air molecules that carry sound to your eardrums have stopped their frantic dance. There's only a deep, impossible silence. A silence so complete it's not just the absence of sound, but a whole new state of being. Looking out the window, you see a bird, wings outstretched, locked against the sky. A perfect, unmoving sculpture of feathers. A car on the street is a statue of metal and glass, its driver a mannequin, hand midway to the radio. Everything you see is arrested in a single, shared instant. The world has become a photograph, but you're somehow inside it. The panic and terror you should be feeling? It never comes. The neural activity that creates thought and emotion is frozen, too. Your very last thought, "That's odd," is stretched into an eternity, an unfinished electrical signal in the maze of your mind. You aren't trapped in time, you are trapped outside of it. You're just another part of the static scene, no more active than the suspended drop of coffee or the frozen bird in the sky. And you're not alone. Across the globe, billions of people are caught mid-stride, mid-laugh, mid-sleep. Every action, every process, every beginning and every end, has been cut short. The world is a museum of its own final moment. The fundamental rule that allows for a before and an after has been surgically removed from the fabric of existence. To understand how this is even possible, we have to ask a much deeper question. What is time, anyway? The science of the stop. What is time? We usually think of time as a constant, forward-flowing river. It's the metronome of our lives, ticking away seconds and years. But in physics, time is something far stranger. It's not just a measurement, it's a dimension. Think about how you'd give directions. You might say 10 meters forward, 5 to the left, and 2 meters up. Those are the 3 dimensions of space. But to really pinpoint an event, you need a fourth piece of information: when it happens. That, when, is the fourth dimension: time. Together, these 4 create the unified fabric we call spacetime. You aren't just moving through space. You are constantly, unstoppably, moving through time. Everything that has ever happened or ever will happen has its own specific address in spacetime. Your birth, the fall of the Roman Empire, the first star igniting, they're all just points on this 4-dimensional map. Motion is simply the path you take through spacetime. A car driving down the road is tracing a line through all 4 dimensions at once. Even when you're sitting perfectly still, you are hurtling through the time dimension. This is a core idea in Einstein's relativity. All objects in the universe are traveling through space-time at one constant speed: the speed of light. Now, that sounds crazy, because we think of the speed of light as something you move at through space. But this speed is actually a budget shared between the 4 dimensions of space-time. The more of your speed budget you use to move through space, the less you have left for moving through time. When you stand still, you're spending your entire budget traveling through the time dimension, which is why time passes at its normal rate for you. But as you start moving through space, you have to borrow some of that speed from your journey through time. The result? Your clock, your biology, everything moves through time more slowly compared to someone who is stationary. This is the famous idea of time dilation. If an object could reach the speed of light in space, it would use up its entire budget, leaving nothing for time. For that object, time would effectively stop. So, what is change? It's just the difference between an object's state at one moment in time and its state at another. Every single process, from a neuron firing to galaxies colliding, is fundamentally a journey through the time dimension. Motion itself is defined as a change in position over time. Without time, there is no motion. When our unseen force pauses the universe, it's halting our journey through that 4th dimension. It's freezing the t in every single equation of physics. Without the ability to move from one moment to the next, the very concept of change becomes meaningless. Every particle is locked at its spacetime coordinate, unable to progress to the next one. That's why everything freezes. Electrons stop orbiting. Chemical reactions cease. The universe stops expanding. The river of time hasn't just been dammed, it's been frozen into a solid block of ice. But this raises an even bigger question. If nothing is moving, what happens to the most powerful influence in the cosmos, gravity? The science of the stop, gravity's new role. For centuries, we saw gravity as an invisible rope pulling things together, just like Newton described. But Einstein gave us a completely new, and frankly beautiful, picture of it. Gravity isn't a force at all. Gravity is the shape of spacetime. The classic analogy is a bowling ball on a rubber sheet. The ball makes a dent, a curve, in the sheet. If you roll a marble nearby, it curves towards the ball not because of some mysterious pull, but because it's just following the curve in the space it's moving through. Now, scale that up. Mass and energy like the sun or the earth tell space-time how to curve. And that curved space-time, in turn, tells matter how to move. The earth isn't being pulled by the sun. It's following the straightest possible path through space-time that has been warped by the sun's mass. That straight path just happens to look like an orbit to us. But here's the crucial part. According to one fascinating interpretation of relativity, a huge chunk of the gravity we experience isn't from the curvature of space, but from the warping of time. Near a massive object like Earth, time itself literally runs slower than it does farther away. This is called gravitational time dilation, and we've measured it with hyper-accurate atomic clocks. So when you drop a ball, it doesn't fall because a force is pulling it. It falls because its path forward into the future is now angled downhill toward the center of the Earth. It's simply following the path of least resistance through curved spacetime. That familiar 9.8 meters per second squared is basically the steepness of the time hill you're standing on. So, what happens in our frozen universe? Time has stopped. Does gravity just disappear? No. And this is where the silent diorama really takes shape. The mass is all still there. The Sun, the Earth, every galaxy, they all still have their mass. And mass tells space-time how to curve. The bowling ball is still sitting on the rubber sheet. The dent is still there. The Sun still creates a massive valley in space-time. But nothing can move through time anymore. Nothing can slide down the hill. The Earth is poised on the edge of falling, but the very thing it needs to fall through time is frozen solid. Its orbital path is locked in place. Its velocity of nearly 30 kilometers per second is meaningless because a second no longer exists. Gravity, the great architect of the cosmos, has become a sculptor of a static reality. The curves in spacetime remain, but nothing can travel along them. The universe is no longer a movie. It's the ultimate still frame, held together by the ghost of gravity. And when we zoom out, the scale of this frozen masterpiece is truly awesome. The cosmic diorama. Let's pull back from that frozen room. We rise above the Earth, a perfect blue and white marble suspended in blackness. Its rotation has stopped. One half is locked in perpetual, searing daylight, the other in an eternal, frozen night. Along the terminator, the line between them, a permanent sunset paints the silent clouds in reds and oranges that will never fade. The moon hangs in the sky, its journey halted. It is simply a fixed point of light. The Earth itself is frozen in its path around the Sun, its immense velocity now just a pointer toward a destination it will never reach. Pulling back further, the solar system is a breathtaking, impossible sculpture. Jupiter's great red spot, a storm bigger than Earth, is a silent, unmoving swirl. Saturn's rings are a perfect, solid arc, each tiny ice particle held in its exact place. Comets are suspended in the void, their tails of dust pointing away from a sun whose solar wind stopped blowing in an instant. The entire solar system is an ornate model, left forever unwound. But this is just our neighborhood. Let's keep going. Out in interstellar space, vast clouds of gas and dust, the birthplaces of stars, are frozen mid-collapse. Protostars, on the very verge of igniting, are held in a state of permanent anticipation, their fusion engines never to be switched on. We visit a massive blue giant caught in its final act, a supernova. But the explosion is frozen. Its outer layers are captured in the first milliseconds of expansion, a shell of incandescent gas that will never travel any further. The shockwave is a static, spherical wall of light. The universe has been robbed of the gold and carbon this star was about to create. We fly toward the center of our Milky Way. Its magnificent spiral arms are now rigid bands of light. The entire galaxy, 100,000 light-years across, is a single solid object. At its heart, the supermassive black hole, Sagittarius A*, is still there. Its accretion disk, a vortex of superheated matter spiraling to its doom, is now a silent, glowing ring. The black hole is a predator in a world where nothing moves. One last time, we pull back to see the grandest scale of all. The cosmic web. We see the Andromeda galaxy, hurtling toward us for a collision billions of years from now. Except now, it hangs in the void, forever 2.5 million light-years away, frozen in a gravitational embrace that will never be consummated. The expansion of space itself has stopped. The universe is no longer growing. It just is. A finished work of art with no artist and no audience. A breathtaking, silent, and utterly final diorama. The paradoxes of a timeless now. In this frozen gallery of impossible sculptures, the laws of physics start to break down in strange and fascinating ways. Take light. Photons are defined by their journey at the speed of light. In our frozen universe, that journey is over. A ray of light from a distant star, having traveled for 1 billion years, is frozen solid in space, a meter from your now unseeing eye. The universe is filled with a ghostly lattice of stationary photons, an image of everything as it was in that final moment. Does this mean the universe is dark? From the perspective of anyone inside it, yes. To see something, photons have to travel and hit your eye. Since nothing is moving, the very act of perception, a process that requires time, is impossible. But what if you could perceive it? You'd be surrounded by a static sea of light. You could, in theory, walk up to a photon and just look at it. The light from that frozen supernova is now a solid, glowing shell you could fly through. Inside, you'd see the star moments before it blew up. Outside, you'd see it moments after. The past, present, and future of that single event are laid out in space like pages in a book. This leads to the biggest paradox of all: consciousness. From a physical standpoint, our thoughts, our feelings, our sense of self, they're all products of motion. Neurons firing, chemicals crossing synapses. It's a dance of change. With time stopped, that dance ends instantly. Your last thought is an unfinished signal. Your consciousness isn't trapped, it's extinguished, because the process that creates it is no longer running. You wouldn't experience an eternity of silence. You wouldn't experience anything at all. The very concept of experience needs time. For the inhabitants of this frozen universe, there's no difference between the first nanosecond and 1 trillion years later. No one is there to count. And what about cause and effect? That bedrock of reality is built on time. The cause has to come before the effect. In a timeless universe, causality is meaningless. The droplet isn't falling because of gravity, it just is in a position below the cup. The chain of why has been broken. All that's left is an infinite, simultaneous what. The universe has become a place of pure existence, with no becoming. An eternal, unchanging now. It's not that the future is unwritten. It's that there is no future left to write. There's only the last page of the cosmic story, open for an eternity that no one can read. The universe is perfect, complete, and dead. The day the universe froze, reality wasn't destroyed. In a strange way, it was perfected, completed. Every particle settled into its final place, governed by the frozen curves of spacetime, a silent monument to its own last moment. This whole thought experiment, while a fantasy, reveals a profound truth about our own existence. We often complain about time, thinking of it as a thief. But the opposite is true. Time is the ultimate gift. It's the engine of change, the source of all motion, the very thing that allows the universe to happen. It's the canvas for consciousness and the condition for experience itself. Without the relentless march of time, there is no life, no thought, no beauty, no meaning. The frozen cosmos is breathtaking, but it's a sterile kind of beauty. A universe without a future is a universe without potential. Our universe, the one we're in right now, is messy, chaotic, and always changing. But it's alive. It's a story that is still being written. Every tick of the clock, every beat of your heart, is a rebellion against the stillness. The ultimate lesson here is a simple one. The flow of time isn't a countdown to an end. It's the very thing that gives us a beginning, a middle, and the precious, fleeting chance to be part of the story at all. We love exploring these huge cosmic what-ifs, and we're passionate about diving into the biggest questions in science. If you share that passion and want to help us make more videos like this one, please consider supporting us on Patreon. It allows us to keep asking these questions. And, as always, if you want to take a deeper dive into the ideas we talked about today, check out the sources we've linked in the description. You won't notice the moment it all ends. What if the universe had an end so absolute that no one could ever see it coming? You might picture a cosmic cataclysm, a final blinding flash, or maybe the universe crunching back in on itself. But the most profound ending wouldn't be something you'd witness. It wouldn't be loud, or bright, or even dark. It would just be the silent, instantaneous end of time itself. Right now, your brain is doing something so constant you've never once stopped to notice it. It's not thinking, or feeling, or sensing, it's processing reality through the dimension we call time. It's the simple fact that one thought can follow another, that you can read this sentence from start to finish. If you stop that one thing, even for an instant, you stop existing. Not die, in the way we normally think about it. Just cease. You wouldn't even know it happened. If time stopped, the very foundation of your consciousness, your ability to experience anything, would vanish right along with it. This means the moment of universal stillness would be a moment you could never, ever have. There would be no transition, no feeling of fading away, no final thought. There would be nothing, because the mechanism that allows for anything to be experienced would be fundamentally broken. This isn't just a philosophical riddle. It's a journey into the bedrock of physics and neuroscience. It's an exploration of what you are at the most basic level. Because to understand why you wouldn't notice the end of time, you first have to understand what time actually is, and more importantly, what it does for you. The physics of a frozen universe. To even begin talking about time stopping, we have to wrestle with what time actually is. In our daily lives, it feels like a river, flowing in one direction, carrying us from past to present to future. In classical, Newtonian physics, that was pretty much the model. Time was a universal clock, ticking at the same rate for everyone, everywhere. It was absolute. But then, a clerk in a Swiss patent office named Albert Einstein came along and completely shattered that idea. Einstein's theory of relativity showed us that time isn't some separate, independent thing. It's woven together with the three dimensions of space into a single, four-dimensional fabric, spacetime. And this fabric isn't rigid, it's dynamic. It can be bent and stretched by mass and energy. This is what we feel as gravity. This means time isn't absolute at all, it's relative. The stronger the gravity you're in, or the faster you move through space, the slower time passes for you compared to someone else. This isn't just a theory, it's a proven reality we rely on every day. The GPS satellites orbiting our planet have to constantly adjust their clocks because time literally runs faster for them in their weaker gravitational field. Without those relativistic corrections, your GPS would be off by several miles after just one day. So, when we ask, what if time stopped? We're really asking what would happen if a fundamental dimension of our reality just vanished. The implications aren't just strange, they are catastrophically absolute. A universe without time would be a static, unchanging universe. Let's think about the most basic parts of reality. First, light. We see the world because particles of light, photons, travel from objects to our eyes. The speed of light is the cosmic speed limit, about 300,000 kilometers per second. But speed is just distance divided by time. If time is zero, then the distance traveled is also zero. The instant time stopped, every photon in the universe would freeze in its tracks. The light from the sun, the stars, the screen you're looking at right now, all of it, suspended and unable to move. The result is immediate and total darkness. But you wouldn't see it go black. The very process of seeing would be arrested. It goes deeper. The fundamental forces of nature, like the electromagnetic force that holds atoms together, all rely on the exchange of particles. Those exchanges happen over time. Without time, there's no exchange. Electrons would freeze in their orbits. Chemical bonds would become rigid. Nothing could react with anything else. Physical processes would halt. Molecules would stop vibrating, meaning the concept of heat would become meaningless. An object's temperature is just the average energy of its moving particles, but motion needs time. In a timeless universe, there is no motion, so there is no heat. The universe would be at absolute zero, not because it's cold, but because the very idea of temperature would no longer apply. Sound, which is just vibrations traveling through the air, would also vanish. Absolute silence would fall, but again, you wouldn't be there to hear it, because your eardrum needs time to vibrate and send signals to your brain. Even gravity, which is the curvature of spacetime, would be altered in unimaginable ways. If you remove the time dimension, what happens to that curve? Physicists don't have a clear answer, because the question pushes our laws of physics to their absolute breaking point. The equations that describe our universe simply don't work without a time variable. Imagine the Earth, spinning on its axis and orbiting the Sun. All of that motion would stop instantly. Everything frozen in a single, eternal tableau. But eternal isn't the right word, because that implies duration. This would be a state of pure isness, with no before and no after. Cause and effect would be gone. This is a world that is fundamentally non-functional. It's a snapshot, a single frame of a cosmic film that has stopped rolling. And as total as this physical apocalypse is, it's only half the story. To understand why you wouldn't notice, we need to look inward, from the cosmos to consciousness. The biology of a frozen moment. The physical universe would grind to a halt, a silent, frozen statue of a single instant. But why would this shut down your awareness? The answer is that your consciousness, your very sense of self, isn't a asterisk thing. It's a process. It's a symphony of biological activity that is completely dependent on the passage of time. Let's start small. Every cell in your body is a bustling city of activity. Mitochondria are generating energy, ribosomes are building proteins, and your cell membranes are constantly transporting molecules. All of these are processes, sequences of chemical reactions, one after another. They take time. If time stopped, every one of these life-sustaining activities would cease. Life, at its most basic level, would be over. But consciousness is more specific. It's the product of the human brain, and the brain does not work in an instant. Your thoughts and feelings aren't static snapshots. They're constructed, moment by moment, by the dynamic, time-dependent dance of billions of neurons. Think about how a neuron works. It communicates using electrical and chemical signals. A single thought involves a wave of electrical activity and action potential traveling down a neuron, causing it to release neurotransmitters. Those chemicals then cross a tiny gap to the next neuron, triggering a new wave. This whole cascade takes time, unfolding over milliseconds. A single thought is a pattern of millions of neurons firing in a specific sequence. It's like music. A single, frozen chord can be beautiful, but it isn't a melody. A melody needs a sequence of notes played over time. Consciousness is a melody, not a chord. Without the passage of time, you don't even get a single, sustained note. You get the very beginning of the first note, frozen at the instant it began, forever silent. Neuroscientists have found that our perception of time isn't handled by a single clock in the brain but as a distributed function across many areas. One of the key players we've studied is a region called the lateral interparietal cortex, or LIP. Here, scientists have found something remarkable. Neurons that seem to encode the passage of time. Studies on tasks that require judging a duration show that these neurons have ramping activity. Their firing rate steadily increases or decreases over the interval. It's as if they're acting like a stopwatch. This isn't just for telling time. It's fundamental to how we make decisions and process sensory information into a coherent whole. Think about what you're doing right now. Reading. Your brain is taking in letters, assembling them into words, and pulling out meaning. This whole thing relies on temporal sequencing. You have to process the letters and words in the right order. This is possible because your brain is constantly using the firing patterns of neurons over time to structure reality. So what happens when time stops? The ramping activity in the lip freezes. The wave of electricity that is a thought gets arrested mid-journey. Without time, there is no sequence. Without sequence, there is no thought. Without thought, there is no you. This isn't a gradual fade to black, like falling asleep. It's an instantaneous cut. The machinery of consciousness would simply cease to unfold. The melody stops not between notes, but in the infinitely small moment within a single note. The very substrate of experience is pulled out from under you. And because the mechanism for experiencing or even being aware of a change has itself been destroyed, you'd have absolutely no way of knowing it happened. The philosophy of an unperceived end. We've established that a timeless universe is physically static and that a static brain is a non-conscious one. But the truly unsettling part isn't that your consciousness would end. It's the stark realization that you would be utterly, completely unaware of that ending. This isn't just an absence of experience. It's the asterisk impossibility of experience. Your conscious experience of the present moment isn't a live feed of reality. It's a reconstruction. Your brain buffers and processes sensory data over a window of a few hundred milliseconds to create what you perceive as now. Your subjective present is always, technically, slightly in the past. Now, think about forming a memory. For you to remember an event, it first has to be perceived and encoded. This involves strengthening connections between neurons, a physical process that takes time. So, let's go back to the moment time stops. At that exact instant, your brain is in its final frame. It contains the neural patterns of your last thought, your last sensation. But for that final frame to be experienced as an event as the moment time stopped, it would need to be processed. A new thought would have to form that represents the asterisk awareness of that final frame. And there's the paradox. All of these things experiencing, becoming aware, remembering require time. They need neurons to fire. In a timeless universe, none of this can happen. The brain is frozen. It cannot process its own final state. The event of time stopping cannot be recorded because the recording mechanism is a casualty of the event itself. You wouldn't experience darkness or silence, because those are experiences. What you would experience is nothing. Not the asterisk feeling of nothingness, but the absolute lack of feeling itself. This idea echoes a fascinating thought experiment called last Thursdayism. It posits that the universe, along with all your memories, might have been created last Thursday, exactly as it is now. All the evidence of a deep past, fossils, light from distant stars, your childhood memories, was created in situ asterisk. The hypothesis is unfalsifiable. There's no experiment you could run to prove it wrong. The moment time stops is the perfect inverse of last Thursdayism. Instead of the universe springing into existence with a built-in past, it would be frozen into a single state with no future. Your final moment would contain all your memories and a sense of a continuing self, but that self would be a static effigy, incapable of perceiving its own stasis. It forces us to ask what we even are. Are you the physical stuff that makes up your body? Or are you the continuous story that runs through your mind? It seems you are the latter. You are the melody. And when time stops, the melody cuts off mid-note. There is no final chord, because the very possibility of a conclusion requires the time in which it can unfold. Thinking about this is a wild ride. It challenges our deepest intuitions about reality. If you find these kinds of thought experiments compelling, and you want to keep exploring the big questions at the intersection of physics, neuroscience, and philosophy, consider subscribing. We dive into stuff like this every week. And let me know in the comments. If the end of everything is a moment that can never be experienced, does that change what it means to experience anything at all? I'm genuinely curious to read your thoughts. What does it feel like? So after all that, the physics, the biology, the philosophy, the most human question is still hanging in the air. What would it feel like? The simplest, most direct, and most profoundly unsatisfying answer is, it wouldn't feel like anything. Our entire language of feeling is built on time. We use words like a sharp pain, a wave of sadness, a flash of insight. All of these describe processes and durations. Even a seemingly instant feeling is a neural pattern that unfolds over milliseconds. Without time, the vocabulary of experience is useless. It's tempting to look for an analogy. What about the time before you were born? You have no memory of that. Or what about going under general anesthesia? Patients often report a sensation of time just disappearing, closing their eyes and then instantly opening them again, hours later. But even these fall short. The state before birth is a before. Anesthesia is temporary. There is an after. You wake up, and your brain registers the gap. You can say, I experienced a loss of time. The stopping of time is different. It is absolute. There is no after. There is no waking up. Consciousness doesn't get paused. Its operating system gets deleted. It's like trying to describe the color blue to someone who has been blind from birth. You can use metaphors. It's cool, like water. But you can never convey the actual subjective experience. They lack the sensory hardware. In the case of a timeless end, we are all that person. We lack the fundamental hardware to process the absence of time, because that hardware is a time-based consciousness. Asking what it feels like is like asking what a silent orchestra sounds like. It doesn't sound like anything. The very category of sound doesn't apply. We can try one more angle. Our perception of time is incredibly flexible. In moments of intense fear, people often report time slowing down dramatically. When we're absorbed in something fun, time flies. These experiences show that our sense of time is a construction of the brain. What if we stretched that to its limit, slowing time down infinitely? Even then, your brain would still be processing, still unfolding its neural melody, just at an incredibly slow tempo. There would still be a next moment. The true end of time isn't an infinite slowdown. It's a hard stop. It's a digital deletion, not an analog fade. An event with zero duration cannot be experienced. So, the question of what it would feel like is a request for a report from a reporter who ceased to exist the moment the story broke. The final, unsettling truth is that the end of everything wouldn't be a new experience. It would just be the point beyond which no more experiences are possible. It would feel like nothing, because feeling is a privilege of a universe where things can happen. We started with a simple question. What if it all just ended? Not in fire, but in stillness. What we found is a paradox at the very heart of existence. The most absolute end imaginable is, by its very nature, an event that can never be known. We saw how physics suggests a timeless universe would be a frozen photograph of a single instant, light stopped, heat gone, the very forces holding atoms together suspended. We journeyed into the brain and found that consciousness is a delicate melody played over milliseconds, a symphony that requires time to exist. And we confronted the philosophical abyss. The realization that an experience of this end is impossible, because the tools of perception and memory are themselves time-based. The witness is terminated along with the event. So, what does this leave us with? Maybe a deeper appreciation for this moment, right now. As you hear these words, your brain is performing a constant, invisible miracle. It's weaving the raw data of the universe into the coherent tapestry of your experience. It's doing the ceaseless temporal math that gives you a past to remember, a future to anticipate, and a present to live in. Our existence is a fleeting dance set to the rhythm of a cosmic clock. The idea that this flow could cease, and that we wouldn't even notice, isn't a reason for dread. Maybe it's a reason for awe. It highlights just how profound and fragile awareness truly is. The end of time is a moment that lies forever beyond the horizon of perception, a silent, invisible wall at the edge of reality. Which leaves us with one final thought. If the end of everything can never be experienced, does that change what it means to experience anything at all? I trapped a moment in a bubble and broke the universe. It was an accident. A total fluke of energy and exotic matter. 1 second, I was calibrating a deep space probe in the quiet, empty void between stars. The next, I'd trapped a piece of eternity in a bubble. A perfect, shimmering sphere hanging right there, where time simply stopped. Light, matter, every quantum vibration inside. Frozen solid. I had no idea that my own curiosity, that simple human impulse to just reach out and touch it, was about to break the very fabric of the universe. Imagine you're floating out there with me, in the vast, cold dark. You see it, too. A basketball-sized globe of impossible stillness. Outside of it, your heart beats, the cosmos wheels on. But inside, a single moment is held captive. This isn't just a thought experiment, this is what happened. And it's a warning. The anatomy of a frozen moment. Before the chaos, it was beautiful. In a strange, terrifying way. I remember the instant it formed. A pulse of energy from my probe's calibration beam hit a cloud of cryopropellant I'd just vented. For a nanosecond, there was a flash of iridescent light, like oil on water, and then it just stabilized. A sphere, about the size of a basketball, hung in space before me, perfectly still. And I don't just mean it wasn't moving. It was fundamentally still. Its surface shimmered with colors that didn't move. You know how the colors on a soap bubble shift and swirl? That's because the thickness of the film is changing, or your angle changes. Here, the bands of magenta, cyan, and gold were static, like a photograph of a bubble. Inside, tiny ice crystals from the propellant were locked in place, not tumbling like they should have been. Perfect, motionless statues. My first thought was gravity. I'm a scientist, after all. General relativity tells us that time slows down near immense gravity. If you watch a clock fall toward a black hole, it seems to tick slower and slower until, at the event horizon, it looks like it freezes for all eternity. Was I looking at some tiny, naked singularity? A flaw in spacetime? But all my sensors were flat. No gravity well, no warping of space. Nothing. It was showing the asterisk effect of infinite time dilation, without the cause our physics demands. It was a paradox from the word go. My mind raced. And then I remembered a weird little corner of quantum mechanics, the quantum Zeno effect. It's named after an old Greek paradox about a flying arrow. If you look at any single instant, the arrow isn't moving, it's just there. In the quantum world, that's not just a riddle. The very act of observing a quantum system can stop it from changing. Experiments have even shown this on a tiny scale, freezing atoms by zapping them with rapid laser pulses. Each pulse measured the atom and reset it, essentially watching it so closely it couldn't decay. Now, this is where my mind took a wild leap, because what I was seeing was impossible. What if that effect, something we've only ever seen in labs on a microscopic scale, could somehow cascade? What if that first energy pulse acted like an infinitely fast observation, locking every particle inside that sphere into a state of not evolving? I know, it's a colossal jump, not supported by any theory. But staring at the impossible object in front of me, it was the only ladder of thought I had. This wasn't a bubble of soap film. It was a bubble of frozen causality. It didn't expand or pop because the forces that would make it do that were themselves trapped in time. For a while, I just watched it. A scar on reality. A perfect prison for a single, meaningless moment. And I, its accidental warden, felt a pull I couldn't resist. I had to understand. I had to interact. The first touch, probing the boundary. Curiosity is a dangerous engine. It's what got us to the stars, and it's what drove me to reach out my hand. What happens when the unstoppable force of flowing time meets the immovable object of a frozen moment? I had to know. I reached out, my gloved fingers moving in slow motion toward the bubble's gleaming, static surface. The moment my fingertip made contact, it didn't go in. It just ceased. It stopped. But my arm, still in normal time, kept pushing. The result was bizarre and horrifying. The molecules on the very edge of my glove, their clocks instantly stopped, froze in place. The molecules right behind them, still moving forward, slammed into them. Imagine shoving your hand into a wall of infinitely dense, frozen time. The material of my glove started piling up at the boundary, atom by atom. Each particle that crossed the line was just added to the frozen picture. There was no give, no entry, just accumulation. I felt this immense, unyielding resistance, like I was pushing against something with infinite mass. Then came the cold. An absolute, searing cold that had nothing to do with the temperature of space. Heat is just the vibration of atoms. But the atoms of my glove touching the bubble asterisk couldn't vibrate. Their time had stopped. All their thermal energy was instantly gone, creating a perfect heat sink. My suit's heaters went haywire, alarms screaming, but the cold was a fundamental property of this broken physics. I yanked my hand back. My fingers were numb, and the tip of my glove was strangely flattened and discolored, as if it had been crushed by impossible pressures. The universe, it seems, had more tests for me. My sensors picked up an incoming asteroid, about the size of a car, on a direct collision course. It was moving fast thousands of kilometers per hour. No time to move. It was going to hit us. I braced for impact, but the asteroid struck the bubble first. What happened next was a grotesque work of art that defied physics. The front of the asteroid hit the bubble's boundary and, just like my glove, it stopped. Instantly. But the back half, still blazing forward, crashed into its own frozen front. The result was a cataclysmic, silent explosion that became an instantaneous sculpture. The impact vaporized the back half of the rock into a cloud of plasma and debris. But the front half was still there, perfectly preserved, embedded in the bubble's surface. Shards of rock were frozen mid-shatter. Wisps of vaporized minerals were suspended in eternal, glowing filaments. A snapshot of an explosion, held forever. This was a monumental violation. What about the conservation of momentum and energy? Where did all the asteroid's kinetic energy go? Some of it blasted outward as superheated gas, but the rest, the energy of the front half of the rock, was just gone. Nullified. Absorbed by the timeless state of the bubble. The bubble now wore a scar. A jagged, unmoving trophy of debris. It was no longer a curiosity. It was a hazard. The problem of light. After the asteroid, I kept my distance. But one question burned in my mind. Matter had behaved paradoxically. But what about something without mass? What happens when the fastest thing in the universe meets a place where time doesn't exist? I aimed the probe's high-intensity laser at the bubble. I shielded my visor, took a breath, and fired. A brilliant, pencil-thin beam of red light shot across the void. And then the universe broke. Again. The photons, the particles of light, travel at a constant c. It's the speed limit of the cosmos. As the front of my laser beam touched the bubble's boundary, it stopped. Dead. I was looking at something that just shouldn't be possible. The light didn't reflect. It didn't bend. It didn't pass through. The photons at the very front of the beam simply halted, their velocity crashing to zero. Velocity is distance over time. If time inside is zero, then what does that even mean? As I held the laser steady, more and more photons streamed out, piling up behind the ones in front, just like the atoms of my glove. The effect was spectacular. I was watching a beam of light become a solid object. The laser beam was stacking up, photon by photon, creating a glowing red line that stretched from the bubble all the way back to me. The energy had to go somewhere. Since it couldn't move forward, it converted into a static, high-intensity electromagnetic field. A solid rod of trapped light. The bubble itself began to glow with a fierce, crimson light, the energy of trillions of captured photons turning the timeless prison into a radiant beacon. I tried to compare it to a black hole, where light is stretched until it seems to freeze at the event horizon. But I knew the analogy was flawed. That's caused by gravity, and this bubble had none. The glow I was seeing wasn't from a gravity well. It was the glow of the laws of physics being systematically taken apart. A photon at rest should have no energy, no momentum, no existence. Yet here it was, a blazing monument to the impossible. The bubble wasn't passive anymore. It was actively consuming the energy of the universe around it. And I was starting to feel less like an observer and more like an accomplice. The nightmare of causality. The experiments with matter and light had revealed the bubble's physical rules. Nothing gets in, and its frozen state doesn't get out. But I started to wonder about more complex things. What happens to the very idea of cause and effect? My next test was born of a terrifying curiosity. I wanted to see if I could pass an object through the bubble. I took a long, thin carbon fiber rod from the probe, about 10 meters long. My plan was to use my suit's thrusters to push it with continuous force, hoping to overwhelm that piling up resistance I'd felt and force it clean through. As I pushed, the resistance was immense, just like before. My thrusters roared. The front of the rod glowed from the friction against the boundary of time itself. But slowly, agonizingly, it advanced. Centimeter by centimeter, the rod penetrated the sphere. I had pushed an object partway into a frozen moment. The rod was now half in, half out. And in that instant, I had created a causal nightmare. Think about it. The 5 meters of the rod outside the bubble were still in my time, aging second by second along with me. But the 5 meters inside the bubble were locked in the single instant they crossed the boundary. I was holding one solid object that existed in 2 different times at once. A bridge between now and a frozen then. Physics has no language for this. A solid object is held together by forces passed between its molecules. But how can a force be transmitted into a region where time is frozen? The chain of cause and effect that holds the rod together should have just stopped at the boundary. The rod should have disintegrated from a causal fracture. But it didn't. It held. An impossibility connecting my present to a frozen past. I had a horrifying thought. What if I pulled it out? Would the part that was frozen suddenly catch up on all the time it missed? Or would it emerge exactly as it went in, now younger than the other half? The paradoxes twisted in my mind, each one more reality-bending than the last. This boundary was a perfect insulator of everything. Sound couldn't cross it. Heat couldn't cross it. It was only extinguished. I thought about quantum entanglement. What if I sent one of a pair of entangled particles into the bubble? Its state would be locked. If I then measured the particle out here, the instant connection of entanglement should force a change in the particle inside. But how can you change something trapped in no time? Does the link break? Or, more terrifyingly, does entanglement work outside of time? I had accidentally created a laboratory for breaking reality, and I was the only test subject. The climax. Breaking the universe. I couldn't leave it there. This bubble, this scar, this monument to my own hubris. It was a violation. Its very existence felt like a ticking time bomb. Every attempt to understand it had only revealed deeper layers of chaos. It consumed matter, trapped energy, and broke causality. My final experiment wasn't about curiosity. It was about desperation. I had to destroy it. My logic was simple, and probably insane. If a little energy was trapped, what would a massive, overwhelming amount of energy do? Could I overload it? Could I pop it? I aimed the probe's main fusion engine directly at the sphere. I overrode every safety protocol, setting it to dump its entire remaining power in a single, catastrophic burst. I backed away to what I hoped was a safe distance, and I hit the button. The probe's engine flared to life in a silent, brilliant flash that outshone the stars. A river of incandescent plasma slammed into the bubble. For a moment, it behaved just like the laser had. The bubble's surface glowed with an impossible, blinding intensity as it absorbed the colossal energy dump. It became a miniature sun. But it was too much. The boundary, that infinitely thin line between time and timelessness, began to flicker. And then it shattered. It didn't pop. It shattered like a pane of glass hit with a sledgehammer. But it wasn't energy or matter that exploded outwards. This is where I can only tell you what I think I saw. What erupted from the bubble was a debt. For its entire existence, the bubble had failed to participate in time. It had built up a temporal debt. And when it broke, that debt was called in. All at once. A wave expanded out from that point. Not a shock wave. A causality wave. It moved at the speed of light, and it didn't destroy. It rewrote. As the wave washed over me, I felt a dizzying vertigo that wasn't physical. It was a wave of pure information, a recalculation of the cosmos. I looked at the stars, and the constellations were wrong. Orion's belt had 4 stars. The Pleiades were a red smear instead of a blue pinpoint. The light from distant galaxies flickered as their entire histories were re-evaluated. The fundamental constants of the universe, the speed of light, the charge of an electron, I had no way to measure them, but I felt in my bones that they had been subtly, terribly changed. I hadn't just destroyed the bubble. I had unleashed its core paradox onto the universe. I had pulled a thread, and the entire tapestry was reweaving itself into a new, unfamiliar pattern. The bubble is gone. The terrible, beautiful light has vanished. But the silence that remains is heavier than before. The stars above me are not the stars I was born under. The universe is just wrong. A cosmic typo, and I'm the author. My journey began with an accident that created an impossible object. It turned into a descent into chaos, where every attempt to understand only broke reality a little more. I started with a question. What if time could stop in just one place? I found the answer. It can't. Not without the universe demanding payment. Now, I'm left floating in the quiet dark with a new and more terrifying question. In a universe where the rules can be rewritten, what is even real anymore? I'm alone, out here, in the cosmos I accidentally created. Einstein's glitch that freezes your friends in time. What if you could watch a friend fall into a black hole, only to see them slow down and just freeze at the edge? Forever. To you, their journey seems to take an infinite amount of time. They become a permanent, frozen statue on the brink of oblivion. But for them? Everything feels totally normal as they slip right past that edge, completely unaware of the time-bending drama you're witnessing. This isn't science fiction. This is a real paradox, a weird side effect of Albert Einstein's biggest ideas. It's a glitch in the fabric of the cosmos that forces us to question the one thing we all think we understand: time itself. So what's really going on at the edge of a black hole? Does time actually stop? And if two people can experience the same event so differently, who's right? The answer might just rewire how you think about space, time, and reality itself. Alright, picture this. You're in a spaceship, holding a nice, safe orbit around a supermassive black hole. Next to you, in their own ship, is your best friend. And they've decided to take the ultimate plunge. You watch their ship peel away, accelerating toward that inky blackness dominating your view. At first, it all looks normal. They wave, you see their engines fire, they pick up speed. But as they get closer and closer to that sharp, dark edge, the point of no return called the event horizon, something impossible starts to happen. From your ship, it looks like they're slowing down. It's not a mechanical failure, it's like they're suddenly flying through cosmic molasses. The light from their ship gets redder and dimmer. The seconds on their clock, which you're monitoring, start ticking slower and slower and slower than your own. Eventually, their ship's forward progress just stops. They are just there, frozen in time, a painting on the edge of the abyss, never quite crossing over. To you, they will hang there for all of eternity, a ghostly afterimage that will outlast the stars. But here's the paradox, the glitch at the heart of this whole thing. If you could get a message from your friend at that exact moment, they'd tell you something completely baffling. They'd say, "What are you talking about? I feel fine. I just passed the event horizon. The view is weird. But my clock is ticking normally." From their perspective, no time has slowed down at all. They crossed the boundary in a perfectly normal amount of time, while for you, that same event takes an infinite number of years. So, who's right? You, the observer? Or them, the traveler? The crazy answer Einstein figured out is both of you. And understanding why unravels everything. The architecture of a monster. Before we can untangle this time paradox, we need to understand the arena itself. The black hole. These things aren't really holes. Think of them as the most extreme concentration of stuff imaginable, objects so ridiculously dense that their gravity becomes an absolute. Einstein gave us a great way to think about this. Picture the universe as a flat, stretchy rubber sheet. This sheet is spacetime, the four-dimensional fabric of reality. Normal things, like planets and stars, create a little dip in this sheet. That dip is what we feel as gravity. A marble rolling past a bowling ball isn't pulled by some mysterious force. It's just following the curve in the sheet made by the ball. So, gravity isn't a force, it's just the shape of spacetime. Matter tells spacetime how to curve, and that curve tells matter how to move. Now, imagine a star way bigger than our sun dies. It runs out of fuel, and the outward pressure that held it up for billions of years just vanishes. Gravity, which has been trying to crush the star the whole time, wins. Instantly. The core collapses under its own colossal weight, compressing all that matter down to a point of theoretically infinite density, a place called the singularity. Putting that on our rubber sheet wouldn't just create a dip. It would tear a hole through it, creating a bottomless pit. That's a black hole. The curve in spacetime is so extreme that it wraps back on itself. Surrounding this singularity is the black hole's most famous feature, the event horizon. This isn't a physical surface you could touch or knock on. It's an information boundary. A one-way door in the universe. The event horizon is the exact point where the gravitational pull gets so strong that you'd need to travel faster than the speed of light to escape. And since nothing can travel faster than light, anything that crosses it, a ship, a planet, even light itself, is trapped forever. This point of no return is what makes a black hole black. It's not empty, it's just that no light from inside can ever get out to tell you what's there. The shadow of the black hole we see in pictures is the silhouette of this event horizon. This hole set up a singularity, making a gravitational prison with an event horizon for a wall as the stage for our time paradox. Because this extreme warping of spacetime doesn't just bend the path of spaceships, it bends the flow of time itself. Einstein's glitch. The warping of time. The idea that time isn't constant is one of the wildest predictions of Einstein's theories. He showed that space and time are woven together into one thing, spacetime. And this fabric isn't just sitting there, it gets bent and warped by mass and energy. This has a huge consequence: gravitational time dilation. Simply put, time runs slower in stronger gravity. This isn't just a fun theory, it's real and measurable. Clocks closer to a massive object tick slower than clocks farther away. Atomic clocks here on Earth run measurably slower at sea level than they do on a mountaintop, where gravity is slightly weaker. In 2022, scientists even measured this effect over a distance of just 1 millimeter. Your head is aging infinitesimally faster than your feet. The GPS satellites orbiting Earth have to constantly correct their clocks because time moves faster for them up there. Without those corrections, your GPS would be off by several miles every single day. If that's what happens with Earth's relatively weak gravity, imagine what happens near a black hole. The gravitational field there isn't just stronger, it's off the charts more powerful. As you get closer, the curve in spacetime becomes a terrifyingly steep plunge. This is the source of the paradox. Let's go back to your spaceship, watching your friend fall in. You can see them because particles of light, photons, are traveling from their ship to your eyes. As your friend gets deeper into the black hole's gravity well, every photon they emit has to fight its way out to reach you. This climb out of the gravity well drains the photon's energy. We see this energy loss as something called gravitational redshift. The light waves get stretched out, shifting toward the red end of the spectrum. To your instruments, the signal from your friend's ship gets redder and dimmer. A pulse of light they send every second, according to their clock, takes longer and longer to arrive. First, there's 1 second between pulses, then 2 seconds, then 10, then 1,000. From your point of view, everything about their ship is slowing down, because the information, the light itself, is getting choked by warped spacetime. As they get right up to the event horizon, this effect becomes infinite. A photon emitted from the exact horizon would be infinitely redshifted, its wavelength stretched to infinity, meaning it has zero energy and is impossible to detect. So, the last photon you could ever see from your friend is the one they emitted just before they crossed the horizon. That last little bit of light takes an incredibly long time to reach you. The result? From your safe distance, your friend's approach to the horizon is stretched out over all of eternity. You see them get slower, redder, and dimmer, until they appear to freeze right at the edge, never quite making it across. Their time, relative to yours, has effectively stopped. And this isn't an illusion. In your frame of reference, this is what is physically happening. The math of relativity even confirms it. For an outside observer, the time it takes to watch something reach the horizon is infinite. The traveler's journey. Inside the glitch. Now for the most important trick in all of relativity. Let's change our perspective. Forget our ship. We're now with our friend, falling into the abyss. What do we experience? The answer comes from another of Einstein's brilliant ideas, the equivalence principle. It says that locally right in your immediate area you can't tell the difference between gravity and acceleration. If you're in a windowless elevator accelerating upwards in deep space, you'll feel pinned to the floor exactly like you would on Earth. You could drop a ball, and it would fall just the same. The flip side of this is even cooler. When you're in freefall, gravity disappears. An astronaut in orbit feels weightless not because there's no gravity, but because their ship, and everything inside it are all falling together around the Earth. This is exactly what's happening to our traveler. Their ship is in perfect freefall. So, inside the ship, everything feels completely normal. There's no giant force pulling them down, no crazy sense of speed. They are weightless, floating in their cabin just like an astronaut on the space station. Their own personal clock, what physicists call proper time, ticks along just fine. 1 second is 1 second. They feel zero time dilation. So as they approach the event horizon, there's no dramatic freeze frame. No wall, no shimmering barrier. For a big enough black hole, crossing the event horizon would be completely uneventful. The tidal forces, the difference in gravity between their head and their feet would be so weak they wouldn't even notice. They'd sail right across the point of no return without so much as a bump. Once inside, though, their fate is sealed. Space-time is so warped here that the direction toward the singularity basically becomes the future. Just as we can only move forward in time, the traveler can now only move toward the singularity. Trying to avoid it would be like trying to avoid next Tuesday. This solves half our paradox. For the person falling in, time doesn't stop. Their clock ticks normally, and they cross the horizon after a finite, perfectly normal amount of their own time. The infinite slowdown is only what the outside observer sees. Both experiences are physically real and correct in their own frame of reference. There's no single, absolute, truth about the time it takes. It's all relative. Spaghettification and other cosmic horrors. While crossing the event horizon of a supermassive black hole might be surprisingly gentle, the journey definitely doesn't end well. The term physicists use for what happens next is spaghettification. This lovely sounding process is all about tidal forces. Imagine falling feet first toward a smaller, stellar mass black hole. The gravitational pull on your feet would be way stronger than the pull on your head. This difference in force would stretch you out like spaghetti until you were torn apart atom by atom, long before you even reached the event horizon. With a supermassive black hole, the horizon is much farther out from the center, so the tidal forces there are weaker. That's why you can cross it in one piece. But as you keep falling toward the singularity, those tidal forces will grow exponentially. No matter the black hole's size, spaghettification is the unavoidable finale. But that's not all. Most black holes spin. And a spinning black hole drags the very fabric of spacetime around with it, like a spinning mixer in a bowl of thick honey. This effect is called frame dragging. Near a rotating black hole, this dragging is so intense that it creates a region outside the event horizon called the ergosphere. Inside the ergosphere, spacetime itself is being dragged around faster than the speed of light. To be clear, this doesn't violate relativity, because it's space itself that's moving. It's impossible to stand still in the ergosphere from an outsider's perspective. You're forced to spin with the black hole, like being caught in a cosmic whirlpool you can't swim out of. Now, here's one final, brain-breaking thought experiment. The rod paradox. Imagine you have an impossibly long, indestructible rod. You're in your safe orbit, and you lower one end of the rod down toward the event horizon. The end of the rod near the black hole is now in a place where time is running much slower than at your end. What happens if you try to push the rod? The signal, the push, has to travel down the rod through regions of increasingly slow time. It would take forever for the far end of the rod to actually move. So what happens? The conflicting frames of reference would put an impossible stress on the rod. Even an unbreakable object would have to break, not from gravity, but because different parts of it are trying to exist in totally different timelines. It's a physical demonstration of the time paradox, showing that one single object can't connect two such profoundly different realities. The grand resolution. It's all relative. So, after all that, how do we solve the central paradox? Your friend falls in over a few hours by their clock, but you see them frozen for eternity. Which one is really happening? The profound and deeply weird answer from general relativity is, you don't have to choose. Both are true. Both perspectives are equally valid in their own reference frames. The universe doesn't have a master clock. There is no universal now that everyone agrees on. That's the whole point of relativity. What you see depends entirely on where you are and how you're moving. The paradox only feels like a paradox because our brains are hardwired to think of time as a single river flowing at the same rate for everyone. Einstein showed us that's just not how it works. Time is local. Time is personal. From your reference frame, the light signals from your friend are stretched out and slowed down to infinity. The information about them crossing the event horizon can never reach you. So, in your observable universe, they never cross it. That's a physical fact for you. From your friend's reference frame, they're in freefall. Time ticks normally, they feel nothing strange, and they pass the horizon after a finite time. That is a physical fact for them. There's no contradiction, because the two of you can never get together again to compare notes. Once your friend crosses the event horizon, they are cut off from your universe forever. You can't send them a message asking, "Why did you freeze?" And they can't send you one back saying, "I didn't." The event horizon is the ultimate firewall, making sure these two totally different, yet equally valid, realities can both exist without breaking logic. This glitch, this freezing of time, isn't a bug in the universe's code. It's the main feature. It's the universe showing us its deepest secret. Time is not what we think. The paradox of the frozen friend isn't just a fun thought experiment. It's what happens when you push the rules of reality to their absolute limit. From your perspective, time grinds to a halt. From their perspective, time flows on, carrying them past the point of no return. The resolution isn't to pick a side, but to embrace the revolutionary idea that there are no sides. Einstein threw out the old, comfortable idea of a single, universal time. In its place, he gave us a universe that's far stranger and more wonderful, a place where time is flexible, personal, and depends entirely on your journey. The glitch that freezes your friend at the edge of a black hole isn't a breakdown of physics. It's physics working exactly as intended. It shows us that reality, in the end, is a matter of perspective. Black holes force us to confront the biggest questions about space, time, and the nature of reality itself. And when we look at them, we're seeing the beautiful, baffling, and relativistic universe that Einstein discovered. We've learned that if you see a friend fall into a black hole, the question isn't, what is really happening to them? The right question is, what is happening to them? According to whom? If this trip to the edge of time warped your brain, consider subscribing for more journeys into the cosmos. And for another look at how time gets weird, check out our video on the twin paradox. Let us know in the comments. If you had the chance, would you be the observer or the traveler? Why stopping time would shatter reality? If you could stop time, what would you do? It's a seductive fantasy, isn't it? The ultimate superpower. A world that holds its breath, just waiting for you. But the reality is a nightmare. Because if you hit pause on the universe, it wouldn't just freeze. It would shatter into nothing. And here's why. Imagine it. You have the one power that beats all others. With a single thought, you bring the whole cosmos to a halt. The city street becomes dead silent. A bird, wings outstretched, hangs in the sky like a bad taxidermy job. A tipped coffee cup hovers, its dark liquid suspended an inch from the floor, a perfect, unmoving sculpture of a small disaster. Everything, from a blinking cursor on a screen to the silent dance of distant galaxies, is frozen in one perfect moment. Your moment. This is the classic fantasy, the superpower we've all daydreamed about. The chance to step outside the relentless river of time. To have all the time in the world to think, to act, to fix a mistake, or just to catch your breath while the world stands still. You could walk through frozen crowds, a ghost in your own reality. You could learn any skill, read every book, witness any moment from any angle. You could become a god in the quiet, frozen cathedral of a single second. It's a beautiful, tempting thought. And it is profoundly, catastrophically wrong. The universe doesn't have a pause button. What we think of as a simple freeze frame is actually a declaration of war on the most fundamental laws of physics. Hitting pause wouldn't just stop the movie, it would set the film on fire, melt the projector, and burn the theater down. The very act of stopping time wouldn't just freeze reality, it would shatter it into oblivion. To understand why, we have to get past our everyday ideas about clocks and calendars and ask what time really is. It isn't some human invention. It's the operating system of the cosmos. And trying to stop it is the one fatal error you can't recover from. The first thing you'd lose in a world without time is everything you use to experience it. The immediate nightmare. Let's say you have this impossible power. And, just to make this thought experiment work, we'll give you a second miracle. A little bubble around you where time still flows normally. You're the only actor on a stage where everyone else has turned to stone. You take a breath, ready to enjoy this new omnipotence. And the first thing that happens is your universe dissolves into absolute, perfect darkness. You would be instantly and totally blind. Vision, our most immediate sense, depends entirely on motion. What we call light is just a stream of hyper-energetic particles called photons. These particles shoot out from a source, like the sun or a light bulb, travel at the fastest speed possible, bounce off objects, and then hit your retinas. Your brain then turns these millions of tiny impacts into a picture of the world. It's a constant, high-speed ballet of particles. The moment you stop time, that ballet ends. Every single photon in the universe freezes in its tracks. Light would no longer flow. It would become a static field of particles, stuck in space like dust in a sunbeam. No new photons can travel from the world around you to your eyes. The world wouldn't just go dark like a room when you flip a switch. This would be a darkness more profound than any cave. It would be the total absence of light, where sight itself becomes meaningless. You could hold your hand in front of your face and see nothing, because the information needed to see your hand can't reach you. So, you're blind. And you're also deaf. Sound is a lot like sight, but instead of light particles, it's about pressure waves. A sound is a vibration. When a bell rings, it vibrates, pushing and pulling on the air molecules around it, creating a wave that travels to your ear. Your brain then translates this motion into sound. But in a time-frozen world, there's no motion. The air molecules that carry sound are locked in place. A scream, a whisper, the sound of your own heart, all of it would be swallowed by a crushing silence. Any sound you tried to make would die in your throat, since the air in your lungs couldn't vibrate to carry it. This silence isn't just quiet, it's the absence of the physical medium for sound. Darkness and silence. But your nightmare is just getting started. You try to take a step to explore this dead world. And you can't move. You're trapped. The air we move through feels like nothing, but it's a chaotic sea of nitrogen, oxygen, and other molecules, all zipping around at hundreds of miles per hour. When you walk, you're pushing trillions of these molecules out of your way. The moment time stops, that sea of air becomes as rigid as a wall of steel. Each atom is locked into a perfectly unyielding, invisible grid. You'd be entombed in a transparent, immovable prison of your own making. Your strength would be useless. You're not pushing against gas anymore. You're pushing against a solid structure with no give. It'd be like being flash frozen in a block of concrete. Even worse, you couldn't breathe. Breathing requires you to expand your chest to let air rush in. But you can't expand your chest against this solid air, and even if you could, the air can't rush anywhere. It's static. You'd be trapped with only the air in your lungs, slowly suffocating. And what about heat? Or cold? You'd feel neither. Temperature is just a measure of atomic motion. The faster atoms jiggle, the hotter something is. Absolute zero is the point where all atomic motion stops. By stopping time, you've basically plunged the universe to absolute zero. Nothing outside your bubble has a temperature. The concepts of hot and cold just ceased to exist. You're in a sensory deprivation tank the size of the cosmos. Blind, deaf, paralyzed, and suffocating in a universe without temperature. In less than a second, your superpower has become the most perfect form of torture imaginable. It's a prison built from the fabric of reality itself. And the reason this prison is so absolute is that you haven't just paused the world. You've violated its most sacred law. The fundamental. Why? The arrow of time. Why is stopping time so destructive? Why does a simple pause cause a total breakdown of everything? The answer is that time, in our universe, isn't a two-way street. It's a one-way road, a relentless forward march. Physicists call this the arrow of time. Think about the dimensions of space. You can walk forward, then backward. You can go left, then right. You can jump up, and gravity pulls you down. But time isn't like that. You can't just pop over to next Tuesday and then swing back to last Friday. You are carried forward, second by second, and you can't reverse course. This forward flow is as fundamental as gravity. But what drives it? The engine is a concept called entropy. Entropy is often described as disorder or chaos. But it's more accurate to think of it as a measure of probability. It's the number of ways the atoms in a system can be arranged. Imagine a box with a divider. On one side, you have a bunch of gas molecules, all neat and tidy. This is a low entropy, ordered state. There are relatively few ways for the molecules to be arranged while stuck on one side. Now, you remove the divider. The gas spreads out randomly until it fills the whole box. This is a high entropy, disordered state. Why? Not because of some force, but because there are overwhelmingly more ways for the molecules to be spread out than for them to be huddled in one corner. The universe is always moving toward the most statistically likely arrangement, which is always a state of higher entropy. This is the core of the second law of thermodynamics, one of the most unbreakable laws in physics. It says that in an isolated system like our universe, total entropy will never decrease. An ice cube in hot tea melts. It doesn't get colder while making the tea hotter. An egg that scrambles on the floor will never unscramble itself and leap back into your hand. In every case, the system moves from low entropy, ordered, to high entropy, disordered. This relentless increase in entropy is what gives time its direction. It is the arrow. The basic laws of physics are mostly time-symmetric. A video of two billiard balls colliding looks fine played backward. But a video of an egg scrambling looks absurd in reverse. The second law breaks that symmetry and separates the past from the future. This raises a deeper question. If the universe is always getting more disordered, that means in the past, it must have been more ordered. Much more ordered. And if you go all the way back to the beginning of time, you must find a state of the lowest possible entropy. That's exactly what our cosmological models suggest. The leading theory is known as the past hypothesis. It proposes that the universe began in an extraordinarily special, highly ordered, low entropy state at the Big Bang. 13. 8 billion years ago, all the matter and energy in the universe was in a state of almost perfect smoothness. While that might sound messy, when gravity is in charge, smooth is actually the most ordered, lowest entropy state. A clumpy universe with stars and black holes is far more disordered. The early universe was like a perfectly wound-up clock. It had no choice but to unwind, expand, and increase its entropy. The formation of galaxies, the birth of stars, the evolution of life all are just temporary stages in the universe's journey from order toward its final, inevitable state of maximum disorder, a cold, heat death. Life itself is a great example. You are a highly ordered, low-entropy system. But you only stay that way by consuming energy and expelling waste and heat, which increases the total entropy of the universe. Your own memories are proof of this arrow. Your brain records the past, lower entropy, but can only guess at the future, higher entropy. So, time isn't an illusion. It's the direct result of the second law of thermodynamics, powered by the unique starting conditions of our universe. Now we can finally understand the true horror of our thought experiment. When you hit pause, you're not just stopping a clock. You are ordering the universe to violate the second law. And that isn't a pause. That's a fundamental break in the operating system of reality. Shattering reality. So what does it actually mean to try and stop entropy? What happens when you challenge the most fundamental statistical certainty in the cosmos? This is where reality doesn't just bend. It shatters. Trying to stop time is like trying to build an infinitely strong dam in a cosmic river made of probability. Its current is the overwhelming statistical drive of every particle in the universe to find a more disordered state. You're trying to hold back the destiny of septillions upon septillions of atoms, all at once. The pressure against your dam wouldn't just be immense, it would be the pressure of near infinite improbability. The universe must move toward higher entropy. Halting this isn't like breaking a speed limit. It's like demanding that 2 + 2 = 5. The second law isn't a rule a system follows. It's a description of how systems behave. But let's say your power is so absolute that it can enforce this contradiction. The universe is frozen. Now for the truly terrifying part. What happens when you press play? The moment you let time flow again, you unleash a paradox that rips existence apart. The paradox of causality. Causality is the simple idea that cause comes before effect. A ball moves because it was hit. A glass shatters because it was dropped. This chain of cause and effect is the narrative thread of reality. Without it, things would happen for no reason at all. Now, think about our paused universe. Let's call the moment before you stopped time State A. Then, you froze everything in State B. Nothing moved, nothing changed. Now, you press play, and the universe enters State C. But what determines State C? Physics relies on the state of things at one moment to determine the next. That link has been broken. The last moment of cause was in State A. The new reality begins from State B, a state that was artificially imposed by you. In effect, the restart of time has occurred without a physical cause. The causal chain has been snapped for every single particle in the cosmos. What tells a photon which way to go? Its prior momentum. But it had no momentum in State B. You've created a universe that is an effect without a cause. You've created a bootstrap paradox on a cosmic scale. This is the moment of shattering. Not an explosion of light and fire, but an explosion of logic. The laws of physics are like algorithms that compute the next state of the universe from the current one. You've fed the cosmic computer an impossible, paradoxical input. You have divided by zero. The result isn't a wrong answer. It's a system crash. The restarted universe would have no coherent information to guide it. Would particles remember their old trajectories? Why should they? That causal chain is broken. Without causality, the universe would unravel into a state of pure, incoherent chaos, a reality without rules, where events have no reason. It would be the blue screen of death for existence itself. The shattering isn't matter breaking apart. It's the logic of reality dissolving into static. It's the end of a story where someone hasn't just ripped out the last page, but erased the language the book was written in. This little trip reveals a profound truth. The relentless flow of time isn't a prison, it's the very thing that makes reality possible. We are not static objects. We are part of the universe's unfolding story, woven into the relentless increase of entropy. The fantasy of stopping time is seductive because it promises control. But the universe is fundamentally uncontrollable. The arrow of time is what allows for stars, life, memories, and consciousness. It is the engine of becoming. The immediate nightmare of a frozen world, the darkness, the silence, the paralysis, is just the first symptom of violating the second law of thermodynamics. The ultimate shattering is the consequence of breaking the chain of causality that law protects. So, the next time you wish for a moment to just stand still, remember what's at stake. We experience reality because it's constantly in motion. To stop that motion isn't to pause the story, it's to rip the pages out entirely. It's to shatter the very concept of existence into an oblivion from which nothing can return. And if you want to explore the paradoxes of trying to go the other way into the past, check out our next video on the grandfather paradox. Our universe when nothing ever happens again. What if the engine of reality just stopped? No more sunrises. No more stars being born. A universe where nothing ever happens again. We're about to explore that chilling quiet, only to find an ultimate truth. If you get rid of time, you get rid of the universe itself. The grand stillness. Picture this. You're holding a warm cup of coffee, watching that delicate plume of steam rise and dance in the morning light. It's a simple, fleeting moment. Now, imagine that dance just freezes. The steam hangs perfectly still, a frozen sculpture in the air. Your heart, which was just beating, is now paused between beats. The entire planet, spinning at 1,000 miles an hour, halts. Everything, from the tiniest atom to the biggest galaxy, is locked in a single, eternal instant. When we ask, what if time stopped? That's the image we get. A cosmic pause button. But a universe without time is way weirder and more paradoxical than a simple freeze frame. To really get it, we have to go deeper. We're not just pausing the movie of the universe. We're destroying the projector, burning the film, and taking apart the very idea of a story. In our lives, time is the river carrying us from one moment to the next. But in physics, time is a dimension, woven together with the three dimensions of space into a four-dimensional fabric, spacetime. It's the coordinate that separates cause from effect. Without it, there's no before and no after. There's no sequence. There is only is. To explore a universe without time, we have to ditch our most basic intuitions. We're not looking at a frozen moment in time, but a reality where the very concept of a moment is meaningless. It's a place where the word happen has lost its definition. This isn't just a thought experiment, it's a look into the source code of reality. And what we're about to find is that a universe without time isn't just a quiet, frozen place. It's a place that could never exist at all. The end of change. The first, most startling casualty of a timeless universe is change itself. Think about what change really is. It's the turning of a page, the aging of a star, the vibration of an atom. Every single process, from a star exploding to a neuron firing in your brain, is a form of change. And change, by its very nature, needs time. It's the move from one state to another. Without time, there's no duration for that move to happen. All of modern physics is built on the idea of change. The laws of nature are just rules that describe how things evolve over time. Take the second law of thermodynamics, often called the arrow of time. It says that things in the universe tend to move from order to disorder. An egg scrambles into an omelet, but you'll never see an omelet spontaneously unscramble itself back into an egg. This one-way street is what seems to give time its direction. But in a timeless universe, that arrow has nowhere to point. There's no forward for disorder to increase into. The universe would be locked in a state of perfect, unchanging balance. Even Einstein wrestled with this. When he first developed his theory of general relativity, he imagined a static, unchanging universe. But his own math showed that gravity would make it all collapse. He had to invent a cosmological constant to hold it up. Later, when Edwin Hubble discovered the universe was actually expanding, Einstein called the static idea his biggest blunder. His struggle shows us something fundamental. Our universe is dynamic. It is a place of constant, relentless change. Let's go deeper. Some theories, like causal set theory, suggest spacetime isn't a smooth fabric. Instead, it's pixelated, built from indivisible atoms of spacetime. In this view, the passage of time is the universe adding new atoms, one by one, creating a new now with each addition. The causal links between these atoms, which ones came before which, define the entire structure of reality. In a universe without time, this process doesn't just pause, it never begins. There's no first atom, because first is a time-based word. There's no growth, because that requires a sequence. The universe isn't a finished structure of these atoms, it's a single, disconnected point. A potential that is never realized. It's a cosmic photograph that was never taken, a story frozen on the first, unwritten letter. Without time, the universe is cast in amber. Nothing moves. Nothing evolves. Nothing happens. The blank slate. Once you stop all change, you stumble into an even stranger consequence. The complete erasure of memory. What is a memory, really? It's just the imprint of a past event on the present. It's the information that tells us a before existed. A crater on the moon remembers an ancient impact. A fossil in a rock remembers a creature that lived long ago. The connections in your brain remember your childhood. Memory is the thread that connects different moments. But in a timeless universe, there are no different moments to connect. There's no before to remember. The very idea of a record becomes impossible. It's like trying to write a sentence. To form a word, each letter you write has to know about the one that came before it. If there is no before, you can't even write the second letter. The page stays eternally blank. This is where things get really weird, thanks to quantum mechanics. For decades, one of the biggest puzzles in physics has been the problem of time. When scientists try to unite general relativity and quantum mechanics, they get a monster of an equation called the Wheeler-DeWitt equation. It's supposed to be the master formula for the entire universe, but it has a bizarre feature. The variable for time is just gone. It describes a static, timeless reality. This has led some physicists to a radical idea. Maybe time isn't fundamental at all. Maybe it's an emergent property, something that pops out of a deeper, timeless reality. One of the most fascinating theories is that time emerges from quantum entanglement. Imagine two entangled particles. No matter how far apart they are linked. Measure one, and you instantly know the state of the other. Now, scale that up. Some theories suggest the whole universe is just a huge network of entangled stuff. In this picture, one part of the universe can act as a clock for another. The change in one part of the web is what we perceive as the passage of time. It's a beautiful idea. Time isn't some cosmic clock ticking in the background. It's the story the universe tells about itself, to itself. But what happens if you just delete the time dimension? Well, those quantum entanglements could never form. There's no process of change for one particle to serve as a clock for another. The very engine that creates the illusion of time is dismantled. Without time, there's no quantum dance. There are no relationships. There's no information being shared. The cosmos becomes a blank slate, with no history, no records, and no memory. We're pushing the boundaries of physics and philosophy here. If these ideas are stretching your brain, consider subscribing and joining our community of cosmic explorers. We get into questions like this every week. Let us know in the comments what you think. Is time real, or is it an illusion? We'd love to hear your take. The Great Pause. So, if our universe has no change and no memory, the next thing to go is motion. At first, that seems obvious. If everything's frozen, nothing is moving. But it's more fundamental than that. Without time, motion is physically and conceptually meaningless. How do we define motion? It's the change in position over time. A car's speed is miles per hour. The cosmic speed limit, the speed of light, is meters per second. Take the per time part out of the equation, and the whole idea of speed just collapses. Think about light. A photon is pure motion. It's born moving at the speed of light and dies moving at the speed of light. From a photon's own point of view, it doesn't experience time at all. Its trip across the universe is instantaneous. But for us, that motion is what connects everything. Light from a distant star traveling for 1 billion years to reach us is a story written by motion through time. In a universe with no time dimension, that story can't be written. Photons aren't just stopped. Their travel is undefined. The universe would be plunged into absolute darkness not because the lights are out, but because light can't go anywhere. This brings us back to Einstein's masterpiece, spacetime. General relativity teaches us that space and time are two sides of the same coin. You can't just get rid of one. In this picture, gravity isn't a force. It's the curvature of spacetime caused by mass and energy. A planet orbits a star by following a straight line through this curved spacetime. So, what happens in our timeless reality? An orbit is a path through space and time. By removing the time coordinate, you flatten the whole geometry. There's no curvature for planets to follow, no paths for galaxies to trace. Even the idea of a reference frame, which lets us measure our motion relative to something else, dissolves. If there's no time, there's no speed. If there's no speed, there are no different perspectives. There's only one, single, static state. Think of spacetime as a novel. The letters exist, but it's their sequence, their progression through the pages that creates the story. Motion is the plot of the universe. Without time, that plot can never unfold. The unhappening. We've now stripped our imaginary universe of change, memory, and motion. And that brings us to the final, devastating conclusion. In a universe without time, there can be no events. In physics, an event isn't just something big. An event is anything that happens. A single atom decaying is an event. An electron absorbing a photon is an event. The Big Bang itself was the first event. In a very real sense, spacetime is the collection of all events. It's a map of happenings, not a map of places. So, a universe with no events? It means nothing happens. Ever. Even empty space is actually a buzzing sea of activity. According to quantum field theory, pairs of virtual particles pop into and out of existence all the time. This quantum foam is a direct result of the uncertainty principle, and it's totally dependent on time. In a timeless universe, that foam is flat. The dice are never rolled. Probability itself stops working. A quantum system exists as a cloud of possibilities until we measure it, which forces it to collapse into one definite outcome. That collapse is an event. Without time, the wave function never collapses. Every possibility stays locked in a permanent state of maybe, never becoming real. The fundamental forces of nature would be useless. Electromagnetism is carried by photons. If photons can't move, the force can't be sent. The strong nuclear force, which holds atoms together, is mediated by gluons. Without the exchange of these particles, no atom could exist. And gravity, as the curvature of spacetime, would be a flat, featureless plane. This takes us back to the very beginning. The Big Bang describes a universe that started hot and dense and has been expanding and cooling ever since. That expansion is a process in time. It's a sequence of events. The first atoms, the first stars, the first galaxies. If you remove time, you remove that entire cosmic history. The initial singularity can't bang, because a bang is an event. A universe without time isn't one where things have stopped. It's a universe where the very possibility of happening has been removed. It's an eternal state of unhappening. The ultimate truth. We started with a simple question. What if time stopped? We imagined a frozen snapshot of a single moment. But as we've dug deeper, that image has dissolved. We've had to peel away one layer of reality after another, only to find nothing at the center. A universe without change would mean the laws of physics are broken. A universe without memory would mean information can't exist. A universe without motion would unravel spacetime itself. And a universe without any of that is a universe where nothing can ever happen. And here's the ultimate twist. That frozen moment we first imagined is a paradox. A frozen moment implies there were moments before it. But we've just shown that if the dimension of time doesn't exist, those previous moments are impossible. The static state we've been exploring couldn't have been arrived at. It couldn't begin to be static. So, a universe without time is not a silent, frozen cosmos. It's a logical contradiction. The existence of space, matter, and the laws of physics are all built on the foundation of time. Time isn't just the box the universe sits in. Time is part of the engine that allows the universe to exist. The answer to the question, what would a universe without time be like, isn't, it would be static. The answer is, it wouldn't be at all. Not a void, not an emptiness, but a complete absence of existence. It's a thought that cancels itself out. To exist, the universe must unfold. To be, it must become. Without time, the universe wouldn't just be empty. It would have simply never happened. The gift of the tick-tock. Our journey into an impossible silence has revealed something magnificent about the cosmos we actually live in. It shows us that time isn't a prison, pulling us towards some inevitable end. It's the fundamental gift of creation. Time is the engine of reality. It's what allows potential to become actual. It's the dimension that gives the universe a story. Whether time is the birth of new spacetime atoms or an illusion born from a quantum dance, the point is the same. The universe is not a static object, it is a dynamic process. It is its own unfolding. This thought experiment gives us a new appreciation for the noise. That relentless tick-tock of the cosmos is what allows for everything. It allows for stars, for planets, for life. It allows for the simple moment of steam rising from a coffee cup. It allows for you and me, for consciousness itself, which is just a story we weave in time. Maybe the greatest mystery isn't what would happen if time stopped, but that it runs at all. Why is there a universe that happens? We may never know for sure. But in asking the question, we awaken to the sheer, breathtaking improbability of it all. The ultimate truth is that we live in a universe with a tomorrow. And that might be the most wondrous thing of all.